Glad to invite today's speaker, Dr. Chetan Singh Thakur, participants and coordinators on behalf of Department of Electronics and Communication, BIT Bangalore. Let me introduce the speaker. Dr. Chetan Singh Thakur, who joined the Indian Institute of Science, Bangalore as an assistant professor in 2017, is also an adjunct faculty at International Center for Neuromorphic System, Australia. He has received his PhD in neuromorphic engineering at Mars Research Institute, Western Sweden University, and is postdoctoral at John Hopkins University, US. He has also worked for a few years with Texas Instruments Singapore as a senior integrated circuit design engineer. His research interest is on to understand the computing principles of the brain and apply those to build a novel intelligent VLSI system. He has received several awards such as Pratiksha Trust Young Investigator Award and an Inspiring Faculty Award from DST for inspired computing. Welcome you, sir.
Thank
Over to
you.
you, sir.
Yeah, thank you, Jasmita. So let me get started. So today's talk would be on, as I said, would be on neuromorphic computing, and the idea is how can we build better intelligent system which is nature inspired, right? Uh, as I said earlier, we would like to have more interactive discussion. So because this is kind of new field, at least in India, and not many people are working. So in case you have any questions, any doubt, feel free to put into the chat window, or maybe you can uh, stop in between and ask questions, because we have 1 hour, so better we'll spend more interactive session, more interactive discussion. So let me talk about this in detail. Let me give you a brief introduction about this. What is neuromorphic engineering or neuromorphic computing? Before we delve into the overall idea about neuromorphic computing, some of the activities in this space in our lab, let me give you that brief idea about it. So neuronics lab is our lab at Indian Institute of Science, which is acronym of neurally inspired reconfigurable intelligent circuits and system. And the overall goal of the lab is to build small low power intelligent machines, right? And this cut across with all the disciplines in VLSI. So we work in the area of digital VLSI design, analog circuit design, FPGA designs, and so on. These are the tools which we use to build this novel intelligent systems. In neuromorphic specifically, there are multiple verticals. One is this neuromorphic VLSI, where we try to understand different pathways in the brain, for example, visual pathways, or auditory pathways, or spatial pathways, right, which is in the hippocampus, and try to understand and try to build those on the architecture, either in digital or analog circuit design. So some of the papers you can find in this space from our website. Another space is neuromorphic sensors and applications. So here we use some kind of uh, sensors which is more biologically inspired. For example, silicon retina is one of the example. You can search about it. Or the cochlea model, which is used in auditory, used as an auditory front end in all this acoustic applications. So these are the two major neuromorphic sensor. One is silicon cochlea, another is silicon retina, we use in our applications. So these are, again, the cochlea model we built in house, and used, as I said, in various acoustic applications. This is more like typical AI application, where we build couple of ML architectures in the lab, different ML architecture. You can search online our latest work in with analog computing, which is Aryabhat is the latest chip which we developed and designed. This is various neural simulators, which is spiking neural simulators, similar to what might have seen in IBM True North or Lohi from Intel. Similarly, we built couple of neural simulators like this, where you can simulate large scale neurons and synapse model. And some of the area is more on the brain computer interface, where you so here in ISC we have this primate lab, where we have this monkey, and we want to connect our neuromorphic system, so that we can record the brain activities from the monkey, and then can you decode what exactly a primate is thinking, and based on that you can take decisions. So these are some of the activities in the neuromorphic space in the lab which we are doing here. Now, what is neuromorphic engineering, right? As I said, this is kind of new and a lot of people might not be aware. So let me dwell into it. So neuromorphic engineering is generally is in when it started in late 80s, and the mandate was to build electronic system which are inspired by function, structure, or physical foundation and signal processing aspect of the brain, right? And there's a saying by Professor Kawamid, who was the founder of this field. As an engineer, we would be foolish to ignore the lessons of a billion year of evolution process, right? So, as an engineer, right, our main motivation to build a system to have an optimal system which is optimal in terms of power, performance, and area, right? This, as an engineer, we always think about this three matrix, right? And if you go back to the brain and see, brain is highly optimal in all these three axes, right? In terms of power, it takes very small power, right, around 20 watts of power, and very small, I mean, it's a large number of parallel distributed connections are there. This is highly optimal in terms of area and performance and as well, right? We are very good in doing all this perceptual task. And the brain is 10 million times more efficient, the best digital technology available. And that's true. We argue here how the brain works a little bit, and how it is different from the current existing technology. So when started this field, there was twofold goal. One is, how can you learn some of those principles which is there in the brain, and can you build some of these brain inspired neuromorphic circuits, which is more on the engineering applications, right? Which is which I just mentioned you. Can you understand those different pathways and build different intelligent system? Another way is, can you build large scale simulators, which I just pointed out, which has the billions and millions of neuron and synapses, and can you ask some scientific questions to simulate that, right? Because the kind of skill which we are talking about, or kind of basic building blocks in the brain, we have like 100 billion neurons and 100 trillion synapses, is difficult to emulate in the conventional computer. So can we build those simulator and ask those scientific questions? So these are the twofold goals of the neuromorphic computing or neuromorphic engineering. So as I said earlier, the mandate was to mimic those basic structure like synapse and neurons, and try to build that on silicon, right? But now the abstraction level has been changed. People have been moving, not only building to function or the basic building blocks, they're also talking about, can we build some system level architecture? Can we build novel algorithm, which is brain inspired algorithm, right? Or spiking algorithms and so on, right? So those are the different abstraction level now people have moved into. Earlier, as I said, when it started around 90s, the basic mandate was just to build the basic function structure like synapse and neurons and axons. And you might be hearing that this neuromorphic system is top 10 breakthrough technology. And also there are several brain initiatives started. One is in Europe, of billion-dollar projects. Same as human brain projects in Europe, and brain initiative in US. And there are several companies working. As I said, IBM's True North was one of the example where they built this neuromorphic processors. And now recently Intel is also there, who built this Lohi chip. Again, you can look into this. And there is a lot of synergies going on in ISC. We have a big group which works in the broad area of brain computation and data science. So before we go into specific applications, let me motivate the audience uh, why it is so important, right? So if you see it simple creature or simple insect, right? So we have this in biology. There, it's a highly efficient machine, and they greatly outperform any man-made technology. And for example, if you take a simple animals, for example, the bee, right, that display fantastic motor skills and cognitive behavior. And if you see, the body weights of that bee is less than 1 gram, and the brain of that bee is few micrograms, right? And the power it consumes it less than 10 microwatts, right? And still it's able to move around in the environment, try to find the potential mate, or try to find the food and so on, right? And how it's able to do in such a low in with such a low power, right? So can we learn something, or can we learn some of those principles and incorporate those into our latest technology, right? So that's the idea. So how nature is doing, can we understand those principles? It's really hard to understand. So the fundamental problem is we don't know how the brain works, right? But still, can we, we still understand some of those basic microcircuits, but understanding the full brain, probably it will take the next century. This whole century probably it has to be dedicated just to understand how the brain works, right? Some of the brain facts which I want to put it here so that you can appreciate about this. The brain is takes, as I said, it takes 20 watts of power, right? And we are so good in doing all this sort of stuffs, in all these cognitive skills, and motor skills and so on, right? And we have around and the total weights of this of the brain is just 1.5 kg, which is 2% of the body weights, but it's very power hungry with respect to the kind of with respect to the body. So it's just 2% of the body weight, but takes 20% of the of energy of the whole food we consume. And it has around 80 to 100 billion neurons. It's a highly dense. 100 billions is a huge amount of basic elements, and very simple. And it has around 100 trillion synapses, which is on an average 10,000 synapses are connected to one neuron, right? So it's a huge, in terms of, as an engineer you can think about it as a huge fan in, right? You have one element is connected to 10,000 inputs, right? So you have 10,000 inputs for one single neuron, right? So huge fan in issues you might end up with if you design any VLSI circuits. And it's very robust and fault tolerant, because every second you are losing a neuron, but still you're very robust in identifying the people. You don't end up with doing wrong things. I mean, in the sense, you don't forget that easily, right? You're still able to perform your daily tasks nicely, even if you're losing a neuron every second. Let me give you a brief comparison between brain versus computer, right? Here, computer means we are talking about the conventional digital computer, right? Where the transistor, the basic unit is a transistor, where this transistor we use as a switch, right? Which is just a binary switch, one and zero, right? And in the brain, the basic computation unit is the neuron, and it's very fuzzy, very imprecise. For example, if you take out a neuron and if you stimulate that neuron, every time you will see different output. Different output means the spike rate of that neuron would be very, very different every time. And so, but in computer, this transistor, if you use as a switch one and zero, it's highly precise, highly you can, every time it will be either one or zero, right? On the brain, the average, it's very slow. This basic neuron, it is very slow. Average firing rate of a neuron is around 100 hertz. Here we talk about in gigahertz and tens of gigahertz speed currently, right? And so computer is more like von Neumann architecture. It's a serial, right? You read from memory, you compute and write back to the memory, right? It's very serial processing. It is more like a parallel, concurrent and distributed processing, right? Each neuron is doing something independently and in parallel, right? It's a highly adaptive and tolerant to component failures, right? As I said, you're losing neuron every second, but still you're adapting of that loss, and still very robust in 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 doing all these cognitive tasks. But here in computer, even if you have billions of those transistor, and if you have few transistor fields, the whole chip would not work, right? And it's not that robust. In the brain, it's completely based on the learning paradigm, right? You just interact with the environment, try to gather the new information and try to adapt those weights or those synapses in the brain, and that's completely based on the learning. It's not like somebody has programmed you, right? Which is conventionally in typical computer is more like a programming kind of paradigm, right? And here in the brain, it's more like a in-memory computing, which probably you might have heard, where the processing and memory is all together. So as I said, right, you have 10,000 synapses connected to one single neuron, and this connection is basically the memory, right? And that's how you store different episodes into that synapses, right? So it's all there together. There's no like separate RAM or a separate computing unit, which is problem, which is commonly will seen in typical computers, right? You have a processing separately and memory separately. Here, memory and processing is all together there. Brain is completely asynchronous. There is no global clock running there, right? It's not like in typical computer you are talking about few gigahertz of clock, which is determining the complete operations in your circuitry, right? But in the brain, it's completely asynchronous. Nobody's driving that as a global signal. The highly power efficient is around 20 watts of power it takes, but computer is not that power efficient. So almost like a million times less efficient if you talk in terms of energy efficiency here. So can understanding of this brain function as an engineer, can we build some efficient and fault tolerant computer? And that's one of the goal of this neuromorphic computing here. And as I just pointed out, the processing and storage is together. So in-memory computing is a kind of recent buzzword where people are trying to use in-memory computing architectures in the literature recently, and that's again inspired from how the neurons and synapses compute, right? So for example, these are the two neurons, and this connectivity is called synapse. This act as a memory. So if you are learning anything or if anything is changing, the synapse changes. So here you store the new information. So whenever one neuron fires, this propagation of a spike basically modulated by this weights of synapse, and then goes that information to the next neuron, and that's why it's called in memory computation here. So storage and processing happen at the same time at the same place, right? So here it's also doing storage and also doing processing whenever this incoming spike comes in. Now, another level of motivation I want to give you in terms of power and architecture, right? So if you see this, even now, even if you, there are a lot of digital emulators are present in the literature, digital neuromorphic emulator. But as I said, evolution has evolved and built a highly efficient machine that greatly outperform any man-made technology, right? And if you see here, in terms of average power dissipations of a biological neuron is 10 to the power minus 10 watt. But now we have a technology which is much lower firing rate, but still we are not able to achieve that kind of complexity. And the reason is, we'll talk about that. So if you see here, the power consumption of a fly brain, right, we just talk about 10 microwatts. And the IBM True North chip, right, which emulate 1 million neurons, is around zero point 0.1 watt, which is much higher than your uh, the fly brain, which has around 1 million neurons, so order of 4 here. Even you are using the latest technology, which which is much more efficient, the single neuron, right? Same is for largest, this spinnaker system, which takes around 50 kilowatts. It's a huge amount of power, even if it is highly optimal than typical CPU. So neurobiology must be doing something special at the network level, right? So at the neuron level we are able to emulate, but at the network level there's a lot of optimizations going on, which we still not able to understand at the brain level. So can we learn something from those principles, and can you build that target? So that's the kind of research going on in this area. So now I want to argue, since you all are coming from VLSI background, as an engineer, you can think about brain as a mixed signal design, where the computation or this neuron which we talk about, the computation is going on in terms of analog domain, right? Because you get the spikes, you compute locally, and that's analog computation. And whenever you want to communicate, the communication is happening in digital. So it's like, that's what I said, it's a mixed signal design where the computation is happening in analog, and the communication is happening in digital, right? Because you are propagating this spike, that's a digital signal. And so why the brain is million times more efficient than a computer? So here I'm talking about computer, means our digital typical computers, right? So if you see, the cost of elementary operation, which is turning on transistor or activating a synapse, is about the same in transistor and in the biology, right? It's around 10 to the power minus 15 joule. But if we when we use since you are coming from this VLSI background, you know, in typical digital signal, whenever the signal propagate from 1010, basically you are charging and discharging a node, right? And that's how you propagate the information, right? So charging of a node and discharging of a node is basically passing of 1 and 0, right? And basically where we lose on almost like a factor of 100 charging and discharging of wires. Another thing is, in digital we use transistor just as a switch, right? 0 and 1, which is kind of very underperformance of a transistor. If you see, transistor is such a beautiful device. If you use the fundamental physics behind the transistor, for example, if you take a equation of a transistor in weak inversion region, the voltage and current characteristics or relationship is exponential. When you go to strong inversion region of a transistor, the relationship is a square function, right? So basically you can easily implement the square function and exponential function by just using a single transistor. However, this is not precise. That's what people have moved into digital computation. But here I am trying to argue the same thing in biology is not precise. All 100 billion neurons are completely different. They are highly mismatched, but still they are able to compute in such a fantastic manner. Even they are doing analog computation. So can we do something there? Because the same thing, if you see at the fundamental physics level, transistors and the basic biological membrane follow the same Boltzmann distribution. So here, but we foolishly, that's what this carbamide say, we pay a factor of 10,000 in energy for taking out a beautiful physics from a transistor and mesh it up to 0 and 1, and then painfully building it back with gates in operation to reinvent the multiplication. So for what he is trying to say here, so for example, if you want to do a multiplication, right, 2 8-bit multiplication, if you do 2 8-bit multiplication, it takes around 10,000 to 15,000 gates, right, and in each gate you have around 5 to 6 transistors, right? So you're talking about 50 60,000 transistors just to do a multiplication. But on the other hand, if you do multiplication in analog domain, just few transistors, right, 4 or 5 transistors is sufficient to do multiplication in analog, right? So but again, as I said, right, in analog it won't be precise, but now here we are talking about, because at the same time brain is also not good in doing big multiplication or doing precise tasks. It's good for cognitive tasks. So can we use analog computation for cognitive tasks? So that's the kind of argument I'm trying to make here. So analog is good as long as you're doing for mainly for perceptual or cognitive tasks. So any question here? I can take few questions before I delve into detail.
Dear participant, you can directly
Sir,
interact with the speaker.
sir, in slide number 9, you have mentioned about storage, right?
Yeah.
Sir, how exactly the storage is working in Synapse?
So synapse is basically it's a either chemical synapse or electrical synapse. So what happens when there's a spike goes on from uh, 1 second. So there is a spike, right? So a spike goes on here, and this synapse is basically, if you model this synapse as a mathematical function, then it's more like an alpha function or exponential decay. So it's more like when you spike goes in, it applies this exponential filter there. You can think of it as exponential decay function, and that the resultant amount of or resultant charge or energy goes into this next neuron. So it's not like just straightforward you do multiplication. So it's some kind of exponential kernel you have here. When the spike goes in, then this exponential function or whatever the function this synapse has, sometimes it's modeled as exponential, sometimes it models as alpha function. And the strength of the synapse is basically what you learn during the learning process.
Is there any chemical reaction or something like that? Storage of data.
So storage is a chemical process, chemical or electrochemical process, I would say. So whenever that spike comes in, there is a lot of vesicles releases, and the release of vesicles are probabilistic. So it's based on the spike rate as well. It depends. So if you read details about the synapse function, you will find these details. But basically, I'm talking in terms of mathematical modeling. What exactly is going on when the spike comes in terms of signal? If you want to understand, when the spike comes in, it applies some kind of exponential function, and this resultant amount goes into the neuron, where you do again some weighted sum here in the soma.
Okay, sir. Do you mean that activation function where it crosses the threshold or something?
That's happening at the soma level
Okay.
here in the next neuron.
Sir,
Yeah.
what are the different deep learning techniques? It will be suitable for low power design, sir.
So deep learning, again, you can call this as a neuromorphic, but it's a little higher abstraction level. So what do you mean by techniques available means here? You mean the architectures or?
Yes, sir. Yes, sir.
So there are in deep learning there are several architecture. One is, again, as I said, you can go into analog domain or again go into the digital domain, right? In
Yes.
analog, you
Yes.
can literally go to ultra low power, like microwatts of power. And there's a
Mhm.
recent work which we did is called but you can talk see that in online. Let's
Okay.
talk about mainly analog computing, where you can literally go much lower power. And there is another thread where a lot of work is going on, digital deep learning architecture. So there
Okay.
is basically what you're modeling. You're modeling a neuron as a weighted sum, right? And then you have some kind of nonlinear function, but this isn't large scale. You're talking about the millions and billions of those elements. So how best you can build with digital architecture? So the idea is, the problem is not computation. The problem is you have a large number of parameters. You're talking about the millions of parameters there, right? So memory is the biggest problem there. How would you read and write from the memory? That's the biggest challenge.
Okay. Thank you, sir.
Yeah. All right. So
Any other questions?
yeah, so here from the neuromorphic perspective, I'm just trying to motivate again why analog is better in terms of if you want to achieve the low power efficiency, right? As I said, the brain only takes about 20 watts of power, right? And that's we are talking about 100 billion neurons, right? But brain is only good in for perceptual task or cognitive tasks. What does that mean by perceptual and cognitive tasks? Anyone answer here? All right, so I'll come to that. So what we are this slide is showing, if you are focusing on perceptual task or cognitive task, then analog is best. But if you're more interested in more precision, where the precision is very very important. For example, if you want to multiply 224-bit number, right, you need very high precision. That way, analog would not be good, right? So as long as you are dealing less than 60 dB of your precision, analog would be a perfect candidate for computation. But above that, analog would not analog would suffer, because you have to maintain those precision, you have to put a lot of energy. So analog would not be good for high precision tasks. And so as I said, what is your perceptual task? So perception uh, task is basically is the process by which we are able to obtain a representation of a natural environment. For example, if you want to do this um, person detection, right, or face recognition, these are all perceptual tasks. You just want to take a qualitative decision, right? It's not something quantitative you want to do, right? Or let's say you want to do this localization of a sound, right? Or you are interested in speaker identification or speaker verification, right? So these are all called cognitive or perceptual tasks, right? Here we are not interested in very high precision tasks, right, as I said. So, and as a brain, we are very good at it, right? We are very good at it in identifying a person. We are very good at in localizing, even in a cocktail party problem, right? We are very good at it in all this various sensory perceptual tasks, right? And that's what even this neuromorphic systems or even this latest machine learning or deep learning are good at it, right? So that's kind of task does not require high precision things. And we just argue in the previous slide, whenever you don't need high precision, whenever your precision is less than 60 dB, analog computing is very very good. So that's what now based on this argument, um, I think we don't have much time, so I will skip this advantage of analog signal processing, and I will come to that why. uh, Okay, before I jump into that, so I'm arguing based on why analog is good, right? Because if you want to go for low precision or cognitive task, analog is perfect for that. And here I just want to give another example. Here, why in neuromorphic system, why we are trying to mimic the biology. If you see the basic membrane in the biology, follow the same Boltzmann distribution as you see in this. So this is the equation of current and voltage in weak inversion region of a transistor, which follows the exponential behavior, which is based on the same Boltzmann distribution, which you will see into the membrane here. Something here you can see this, and same you will see here, same kind of distribution you will see here. So this is the fundamental principle behind developing all these neuromorphic circuits. So if you see, most of this neuromorphic circuit is developed in weak inversion region of a transistor or subthreshold region of a transistor. Now let me talk about a project, a specific project where we use those principles and build some of these VLSI circuits. So this is mainly, as I said, we are focusing on for low power application, right? So we use in weak inversion region of a transistor where we see this exponential behavior. So this is one of the architecture which we built. So this is based on this project inspired from the neural population coding hypothesis. You can search for this, what is neural population coding hypothesis. So in population coding, what happens, neurons in the brain encode information in a collective and distributed manner in a large number of different neurons, right? So here if you see this is our architecture which we implemented into with analog circuit. Here you will see this, it encodes your input stimulants into large pool of non-linear neurons, right? And here you will see these weights are random weights. And there are also similar experimental evidence about random connection in the olfactory system with respect to their order tuning. So if number of hidden notes are very high, then it becomes universal approximator. and then only we just need to train this output weight. So this is kind of simple 3-layer architecture which you build with analog circuit, but it has a direct relation which is found in the olfactory glomeruli. And you can see this paper which talks about this random projection. We use the same random projection here. So but here what interesting things we did here. So if, since you are all having this VLSI background, you know, in analog you have a huge problem of device mismatch, right? Whatever, even if you make billions of transistor, not two transistor would be the same because of this physical fabrication process, right? But in digital it's not a problem because we have a big noise margin there. But analog, everything is important, right? All the states are possible states. So this device mismatch is a biggest problem in analog circuit, right? And that device mismatch is nothing but act as a random weights in our architecture here. So instead of storing these weights, it's by default come randomly because of the fabrication mismatch, right? So that's the kind of key innovation we brought into here, and even we filed an IP on that. It's a very old projects, but the idea is directly we take this inspiration from what we found into this olfactory systems, and we build this architecture where these weights are random and where we exploit this random weights coming from the device mismatch. So that's the key idea here in that. And to learn any function, we just need to train this output weights here. So in this case, in biology also, if you see the tuning curves of a neuron, they generally follow this 10H or sigmoidal kind of behavior, right? And this you can easily implement with this differential pair architecture, where this is your V reference, some reference voltage, and this is your input. So when you sweep this input with constant Vref, the current would follow this 10H behavior or sigmoid or 10H kind of behavior. You can see this saturation kind of non-linearity, which is commonly will also seen in the biology, right? And this is again, as I said, it's working in the weak inversion region. So we are talking about here, here's a few nanoamps of current. You can see this a few nanoamps of current, right? And as I said, we are exploiting this device mismatch here, which is present here. So we don't need to store these weights. This comes because of the mismatch between this M1 and M2 transistor, also because of the mismatch with this M3 transistor, right? So now total we have around 456 neuron, and each neuron will be having different mismatch and offset, right? And that mismatch and offset act as a random weights in our architecture. So we don't need any separate storage. We just uh, use this natural mismatch which is coming from the biology, from our architecture, which is similar which we found in the biology, right? So this offset between M1 and M2 gives you the random offset, and this M3, this mismatch here will give the kind of random mismatch here, or random weights you can call it in this case. Now this is for one input. If you want to have multiple inputs, basically you can create this kind of weighted average circuit where you have a multiple input V1, V2, Vn, and you can have this again differential pair architecture. And then you can and so this is the symbol of this, and this is for two input. This is how you can build it, right? And we use for both n type and p type weighted average circuits. Again, this is weighted average. Again, you need these weights are random, so which is again comes from gm of this transistor, which is nothing but coming from this bias from this transistor. And this bias, again, even if you put the same, because of the mismatch, is all would be different. So gm of each one would be different. So again, we don't need to store this weights as a separate. It comes by default from the random mismatch. And just to train for any circuit, we just need to implement this output weight, which is nothing but an R2R ladder, which is we implemented with the simple R2R DAC here. But this is all for 456 neuron we have to implement. This is the complete chip which we built in 65 nanometer process. It's a 1 mm square chip and with 1.2 volt supply. And you can see here the power number we are talking about is a 3 nanowatts power we get from each neuron. Also, the total power is few microwatts only. And you can see this is such a big circuit. So we have learning rule is also implemented on chip here. So you can learn on the chip itself. This is for multi-input architecture where we use this kind of weighted average circuit. So this is another chip which we implemented in. So this is in 130 nanometer. The second chip is in 130 nanometer where we have two inputs. Again, because of the what we did for each neuron, we are giving the same input, but you can see it's a different tuning curves because of the random mismatch, and that's what we want. And these are some of the results, because we have only 2 inputs, so we can give only 2 features here, and we are able to do this some nice simple classification task here on the chip directly. There are some of the regression tasks. This is the target, this is what we have learned from the chip. And then next what we did, we use this memristor. uh, I'm not sure whether you have heard, but this is like a kind of emerging memories. So we have this built with our collaborator here, the memristor circuit, right? So instead of this output weights, which I've shown here, where you need to, so instead of this whole circuit, right, output weights, we just replace this with the memristor. And then because memristor can store multi-states, right, in instead of so typical memory you store only, for example, SRAM just store 1 or 0, right? But memristor is kind of analog memory. We try to use it here, where we can store instead of 1 bit you can store maybe 7 bit or 8 bit, or it's a multi-state. So in this memristor architecture we are able to store 80 different states. So let me explain what is this novel synaptic device. So this is a floating gate based 2-dimensional analog memory. So it's based on the 2D material, where we utilize for storage of weights. And this memristor device is fabricated from ultra thin to 2-dimensional MOS2 layer. This is a single atomic layer, right? And this is a hexagonal boron nitride dielectric on top of this. It can have 80 different states here, and by basically this layer of graphite act as a floating gate here, and the tunneling of charge between channel and the floating gates enable the storage of information. So here you can see, by giving different spike pulses or different pulses, the different states you are able to store here. Same you can see here. So the idea here is, in a single device you can store different number of states. And we are also shown simple learning rule here is called STDP, spike timing dependent plasticity. It's a biological process that adjusts the strength of connection between neurons in the brain. And here you can see this is kind of STDP learning you have seen in this kind of devices which we built here. And the observed energy you can see here is in picojoule, right? So you can see it's a very small if you want to go for ultra low power applications. There are some of the results which we did. The next what we did, so earlier I've shown here we put this memristor device. Next what we did, we change is for multi input, instead of using weighted average circuit, we use a single transistor, right, where we have capacitive coupling. So it's called multi input floating gates transistor, where instead of single gate you have multi inputs, right? So now from a single input transistor, now you have multi input. So this is not fabricated, this is based on the simulation results, but it allows you, instead of using this so for example, so instead of using this multi inputs, right, here you need a very big circuit if you want to add multiple input. But can you do this with single transistor? So in single transistor you can have a coupling which is coming from this different capacitive coupling, and that can act as a weighted average, which we are doing in the earlier using a circuit. But now single transistor can do that. So that again we did, and so this is now your new differential pair which has multiple input here. And now we are able to get this similar kind of 10H curve. And again, so this is based on simulation. The previous results all were fabricated, chip fabrication. And again we did this with memory simulation results, which we got some decent accuracy here at the chip level. So those are some of the analog circuit results. But we, as I said, we do multiple we have multiple verticals in the lab. So one of the vertical is kind of Aryabhat chip here, which is completely analog. You can search for this chip online. There is a lot of details about this chip. This is we built in 180 nanometer process. And this is the idea is, can we build something like FPA kind of architecture, field programmable analog array kind of architecture. So this is completely analog chip. We have another architecture which is still not published. We call Raman reconfigurable sparse architecture. So this is completely digital. So even we have a FPGA architecture which we have implemented some of the applications, for example, visual wake word or keyword spotting, and that's completely digital. Some of the work which we do in TinyML space, where we use MCU microcontroller, simple microcontroller, and we have demonstrated some of the application for vision, IMU, and acoustic, or also in the space of radar. And one area, one vertical is this hybrid architecture with emerging devices, which I've just shown about the membristors. So these are some of the other applications which we have been doing in the lab. So I can take some more question if you have. This is some of the detail about RD, but since I am talking about analog, let me give you a little brief about this chip. So this chip is like 6 square chip, which has multiple core here. And the key feature of this chip is, so RABIT stands for analog reconfigurable technology and bioscalable hardware for AI tasks, right? So the cool thing about this particular chip is the technology is scalable. So the same technology we also build for 7 nanometer process. We just simulated because we can't afford 7 nanometers. It's really costly. Second thing is the bias scalable. So same transistor you can do in weak inversion region or mid inversion region or a strong inversion region of a transistor. So that's a very cool thing, and I think nobody has proposed so far this technology in bias scalable in analog computing. Second is thing, the third thing is very robust to temperature, because the kind of architecture we built, it's a temperature robust, and it's more like an FPA architecture. So it's a programmable, similar to the FPGA, but still we are doing testing. So still not complete testing is done. Only few results are out, and we are writing few papers on that. So these are some of the details about this RA chip. I think that's all I have, but I think we can have more interactive discussion today. Uh, if you have any question, I'll stop here.
Sir, where the fabrication was done?
So this is in TSMC.
Okay, continue, sir.
Sorry?
You can continue, sir.
Yeah.
Sir, the
It's a TSMC 65 nanometer. The first chip, the second chip was 180 nanometer. Both are TSMC process.
One question they are asked in the chat window, sir.
Yeah, I think I have already answered. Which technology library you use? So
Yes. Only that.
sir, where the fabrication was done? Fabrication.
TSMC. TSMC is fabrication process. Is that answer your question, or you're asking something else, Ajay?
No, do you have fabrication center in IAC?
No. ISC doesn't have that fabrication facility for chip. So TSMC is semiconductor, Taiwan Semiconductor Manufacturing Company. Do you know TSMC? Have you heard TSMC?
No, sir, no.
TSMC should search this. The tool we use, this cadence tools here to develop this.
Sir, just to ask, how much was the cost of this chip, sir?
So 180 nanometer is still okay for this, around 6 to 7 lakh. But 65 nanometer currently we are planning. So that's for 10 mm square, 65 is around 35 lakh. It's really, really costly. Yeah.
For 50 dice, sir, or how many dice?
Dies is 25.
Okay. And 35 lakhs you said for?
That's for 65 nanometer process for 10 square chip.
Oh, okay, 10 square. Okay.
Yeah. Depends on the size and technology. If you
Yeah,
go to
yeah,
lower and lower process, it's much costly.
yeah. So, sir, just one more question. If we want to contact, it is through the website or how to contact? Because I tried once, but it was hard to get in touch.
Contact whom?
This TSMC guys, it is from the website only that they reply. Through website only we
You
have to
need to
contact.
sign an NDA first to get the access to the technology.
But sir, we have to get in touch with a representative from there, right? So,
Yeah. So one thing you can contact Muse Technology. There's a Muse Technology. So they are like a third party.
okay. So
Yeah.
NEWS News
Or
Technology.
Muse. Yeah, Muse, or also you can contact Euro Practice.
Okay. Fine. Okay, got it.
They would help. They are like a third party.
Yeah, because I found it is had to get in touch with somebody from there, foundry
No,
lab.
TSMC won't contact you.
That's what. So you through Euro Practice or News Technology?
Yes.
Yeah, that's what. Okay, sir. Thank you.
Yeah.
Participants, any more questions?
In the Arivata, you have shown 8 cores, right? 8 cores.
Yes.
How the communication is happening? It's a network on chip.
Yeah, correct. Everything is like hardware now. It's an analog company. There is no separate communication protocol. You have to hardwire everything here.
Initially,
If there are no more
my
questions, now
hello,
it's
sir.
time for short break.
Okay.
We'll reassemble at 11:30.
Thank you
I
very
think-
much, sir.
Okay, no problem. Thank you.
Thank you, sir.
Thank you.
Seeing is a different topic, that is biomaterials, which is completely different of what we saw yesterday. These biomaterials play an integral role in the medicine today, restoring function and facilitating healing for people after, for example, injury or disease. Biomaterials may be natural or synthetic and are used in medical applications to support, enhance, or replace damaged tissue or a biological function. So nowadays, doctors, researchers, and engineers use biomaterials for many range of application. Example, medical implants, including heart valves, stents, and grafts, artificial joints, ligaments, tendons, healing loss implants, dental implants, and devices that stimulate nerves. And many such applications are finding, think they my biomaterials play a lead role. So today we have with us Dr. Jisha, who completed her research in the area of materials, and she'll be telling you about what is a biomaterial, why biomaterial, and what are the things required for proper functioning of biomaterials when it goes into the normal human body. uh, her research topic has won us like funding in Serb Power Grant, and she has patent, and she has published her research in many of the reputed journals. So over to you, Jisha.
Thank you, ma'am. Am I audible?
Okay. Yeah, you can continue. Please share the slide.
Yes, madam, it's audible.
Yeah. Okay, I'll share the slides. It's visible.
Yes, madam, it is visible.
Yeah,
Make it screen,
share
big screen.
service.
Yeah, it's visible now, sir.
Yes,
Yes,
madam.
yes.
Thank you, Suna ma'am, my guide, my mentor, for giving me an opportunity to talk on biomaterials. So I'm Dr. Jisha, Assistant Professor from Department of Medical Electronics Engineering, BMS College of Engineering, Bangalore. And under my guide's mentorship and guidance, I've completed research work on biomaterials for the usage of biomaterials for making a rapid malaria sensor for detecting malaria from birth of malaria patients. And our major research works are concentrated on using biomaterials for different sensing applications. So today's session is just to give a brief idea about biomaterials and how do we, what are the available biomaterials, how do we test them, and what is the term biocompatibility, and also how can we do different ways of do the biocompatibility testing. And the remaining will be covered in the coming session. So this is just an introduction to biomaterials, their applications, and biocompatibility testing. So, as we, like most of us, we know that biomedical is completely a multidisciplinary science. This is a combination of different areas of science coming together to achieve some certain specific application, especially in the area of a biological field. So usually when we talk about biomaterials, we include molecular biology, biology itself, including cells and tissues, and we also see the biophysics part. We also see what are the medical science that is directly which is using in the body. So it has to be coordinated with even medical science, and we also should know chemistry, because when we generate some biomaterials, we should know how the material atoms or the materials will react and how they produce biological or biomimetic substances which can be completely used for medical applications. And also material science and engineering is the core half of the biomaterials. So these all together completely from biomedical as a multidisciplinary. We can call it as a complete multidisciplinary science or research area. And so when we talk about the biomaterials, so what is the definition of a biomaterial? So biomaterials, we can say any material which can be natural or man-made, or that comprises whole or a part of a living structure, or a biomedical device which performs or augments and replaces a natural function. So as from the definition itself is very deep. So which say, like as we can see from that, it can be any material, it can be an artificial or a natural or a synthetic, so or any material which has a property to and or join with any living tissue or an cell and work with human body to achieve a certain particular biomedical application or a human body or mimic any organ or support any organ or do the function of a particular organ in the human body, doing the natural function of any body part. So we can call that material completely as a biomaterial. So it's a non-viable material usually used in any medical device. It can be inside the body, or it can even interact with the internal biological systems, or as well as it can be used outside the human body. So before going into the in detail into the biomaterials, so I'll just have to talk to you about the history of biomaterials. So this from where we have started. It's not like it's a recent research area. The use of biomaterials has started from 2000 BC, and the people have used linen threads for wound healing, that is to suture the wounds. They have used linen thread, then metal structures with golden wires or golden plates for cranial fracture. And also bamboo dendron plants were used by Chinese people in 200 BC, near to 200 BC. And also, we might have seen in histories or the previous reports of that, the artificial iron tooth were also used by in ancient times for replacing as dental implants, even though they were not aware that these are used as being a biomaterial. So even iron has started using in the earlier time for an artificial teeth. And later on, coming to the 16th and 19th century time, people have started as research has happened, and metals were used for hard tissue replacement. And we can effectively say the use of a conventional biomaterial use for a biomedical application has started in the year 1939. So Ratner and Sack are two scientists. They have used the polymer, we can say cellophane, as the polymer is the implant material in the year 1939. So this was used for wrapping some blood vessels
ಈಗ ಮಧ್ಯಾಹ್ನ ಇಟ್ಟಿರೋದು ಇದು ಬೆಳಗ್ಗೆ ಅಂದ್ರೆ ಏನು ಮಾಡಲ್ಲ ಅವರು.
aneurysm. So aneurysm is nothing but swelling of the nerves or swelling of the aorta or the vessels, blood vessels. So now to stop the aneurysm, people in 1939 doctors were used to tie or cover those particular blood vessels properly, and so that they will not further swell or expand more and create some stroke in the patient. So in 1939, people have used Teflon made a polymer-based, cellophane-based implant material for covering the blood vessels. And in, later on years, biomade materials are being introduced. Cobalt, chromium, molybdenum, or titanium alloys have come to the picture. They have been used for dental implants, bone joints or hip replacements. All those things we have started using the metal alloys because they are very strong, they are more inert, and they have more biocompatibility. So we switched slowly from metals to metal alloys. And in the year 1970, again we started using another material has come to the picture, which is bioactive, bioresorbable materials. We call them as ceramics, as well as we have started using polymers also. So ceramics are very strong materials which can withstand high stress and strain, which can be used in the body for support function, as well as polymers for other covering or protecting the implants against further corrosion, all those things. So again, when we recently, if we talk about the recent advancement in the area of biomaterials, so now we are in the stage where we are using biomimetic materials like hydrogels, and we also have technologies like 3D printing, 4D bioprinting, so that we can use these biomimetic materials and print our own whichever organs or any other part of the body, so that we can use them as implants in the body directly. So we have a lot of methods like electrospinning and bioprinting methods by which we use artificial organs using biomimetic materials like hydrogels or bioinks are used for these kind of particular applications. So, what are the major properties of biomaterials? When you want to use in a body, you should see, they should be having a certain specific properties. We cannot use any material which we get in the nature or which we make in the body, because they have to have certain properties to be used as a biomaterial. So, if you say the biomaterial properties, the mainly we look at these four properties. One is it has to be a biocompatible material. Another one is it should be anti-infective. It should not cause any infections to the body. And third one is it should have some controlled release mechanism, and it should be an anti-inflammatory. These are the four main properties when we look into a biomaterial, when we will check for only these, mainly for these four properties. So when you say biocompatible, the word itself is a complex term, because it stands for that the material, whatever we are using in the body, the body should not treat this material as a foreign object. So it should be properly work with the organ or implant or with the body fluids and body cells without creating any carcinogenity. And also it should be hemocompatible. So our body fluid, the major body fluid in our body is the blood. So whatever material we will be using, it will be working in connection with the blood supply system or our cardiovascular system. So the material what we are using for any implant or any organ or as a biomaterial should be hemocompatible. That it should not or make the blood to clot, or it should not corrode when it will come in contact with blood. And also we should have a systemic toxicity, that is, it should not create any toxicity in the biological system, and it should not, genotoxicity should be minimum, that is, it should not create any harm to the genes present in our body, and it should not create any dermal sensitization, and it should not also kill the nearby cells in the body when we are using such an implant of a material which is made up of a biomaterial, and also should not cause any irritation to the body. So these are all things we will address in the property called as biocompatibility. So if a material is biocompatible, means it will have less carcinogenity, it has good hemocompatibility, less system toxicity, less genotoxicity, less sensitization, less cytotoxicity, and it will not cause any irritation. So these are all things we will test clarify that this particular material has all these properties, then we call it as a biocompatible material, then it can be suitable to use in a body for making an implant or a tissue or any other functioning. And also, another property when we are talking about biomaterial is nothing but controlled release of material. So biomaterials are mainly used for making implants as well as for drug delivery also. So we can, through using these materials, we can treat some of the issues in the body and we can have a controlled drug release through these materials. So we have to check for the growth factor release, the cell encapsulation, its bioavailability, and drug delivery. All these things will be checked when we check for a controlled release of the material. So it should not create further issues in the body. Whatever function we are intended to give through that material during the drug delivery should be happen only if it has the property of a controlled release mechanism. Another one is when we are talking about, it should be anti-infective. So that is, it should not create any pH variation in the body. It should not cause any intrinsic effects or integrative additive effects in the body. And also it must be biodegradable. Some of the material will join with our body slowly, and it will become a part of our body, and or it should not be treated as a like, if it is not degradable, further it will stay back, it can cause further problems in the body. So we say it just be more like a biodegradable material when we are using it inside the body. And also we should have antimicrobial fillings, anti microbial biomaterials has to be checked for their properties, that is, they are safe to use in our body. They will not cause any further infections into the body. They will not introduce any microbial microorganisms into the body. So for that, we all will check the properties like anti-infective properties of a biomaterial. And the fourth one is nothing but anti-inflammatory. That is when it will come in contact with when you come in contact with the body, it should not create any cross reactivity. It should not increase any more, like react with the water content, and it should be create any endotoxins into the body. And also we have to check for the crystallinity of this particular material in the case of an anti-inflammatory property. So, based on their origin, since biomaterial we can mainly classify into two groups. So, one is natural biomaterials, another one is man-made, or we call it as synthetic biomaterial. So, natural biomaterials have been employed since many years. As I have shown the history, we have used gelatins or hyaluronic acids or heparin or alginate, etc. Moreover, natural biomaterials we cannot use it for a high or a large production or a large scale manufacturing of the implant. So due to this requirement in the high quantities, so we went to synthetic biodegradable polymers or biodegradable materials, which are now consideration in consideration, so that we can have a easy manipulation of this material as well as large scale production of this materials. So basically all these biomaterials we are broadly classified into four groups: polymers, metals, ceramics, and other natural metals, which are naturally existing in the so, and also there is a fifth group of biomaterials which are called as composites. So composites are nothing but if you are combining the properties of any of this material, that is, if you are mixing polymers with metal and making a new material, we can call it as a composite. Since you have the properties of both polymers and metals, so that we can like the stiffness or the tensile nature of the metal and the flexibility of the polymers, we can combine together to make a composite which can be applied for some specific applications. So similarly, we have ceramics can be combined with the metal or polymers to make them more strong, or the less brittle characteristic of ceramics can be added with the other characteristic of polymers to make it more strong material. We can apply it for load-bearing applications, all those things. Similarly, these are all synthetic materials can be mixed with any of the naturally existing material to make composites. So composites are a fusion of all these basic four types of materials, and using these composites we can achieve so many specific applications where we can combine all the advantages of these materials together to create a new smart biomaterial. So we'll see in detail what are the basic features or advantages, limitations, and applications of all these four groups of materials. So when we say biomaterial, the first classification comes is the metals. So metals are mainly used in our body as implants based on titanium and its alloys, silver electrodes or silver or gold materials we will use for many implant applications, and also we go for stainless steel rods or implants for certain applications. So the advantages of metals are there. They have enough stiffness, outstanding tiredness resistance, that is they can bear the load for such a long time. They have enough tensile strain and compressive stress, etc. So that we can make them in any of the, since they are very tensile, we can change their shape and we can make joints or implants which are often exactly in the same structure as we required in our body, that can be achieved through the metals. And the limitation is they are not having enough elasticity. So we cannot stretch beyond the limit. So there has some certain stress limit. So beyond that, it will start, it may become brittle or it may break, and it can be destroyed by rust. That's another issue. So body fluids are mainly alkaline or acidic in nature, and when it will come in contact with these metallic implants, they can easily get corroded if they are not in an inert nature, and they don't have much density, and we need complex procedures to prepare or to make these metals to mold in the shape what we require to use in our body. So also we have some applications for these metals, like usually we use it for weight tolerating implants such as bond plates and pins and screws, also dental root implants. Many of us might have done the dental implants, so where we will be using such metallic parts, and also we use it for knee or joint replacement, and also for wires to tie the bonds or to stitch the bonds together. So for all those things we will be using metals and metallic alloys. And we also have the next group of elements is biomaterials are ceramics. So usually alumina, zirconia, hydroxyapatite, all those things comes under the group of ceramics. And they are very eco-friendly to living tissue. So because they are very highly inert, so they will not cause any harm to the, or they may not react with our body fluids or tissues. And they have enough vigor and firmness. Then they also have enough resistance to rust and wear and less density. And the limitations are not very hard, so they are not flexible, and they are less tiredness resistant. That is, they cannot bear the load for a long time. They may brittle or they may break. So they have a variable mechanical vigor mechanism in the case of these ceramics. So usually ceramics or alumina or zirconia based materials are used for covering for load bearing implants, medical sensors, dental and orthopedic implants. We are using alumina based or zirconia based materials. Now, we have the third group. The third group is nothing but the polymers. So, I am such areas so much close to these polymers. We work on polymer nanocomposites. So, the polymers mainly used in the biomaterials, we can say examples like nylon, silicone, polyester, etc. are the examples of polymeric biomaterials. And they usually have the advantage of eco-friendly to the living tissue. They have enough resilience, less load bearing. They won't do, from their part, they won't induce much load into the biological system. They are simple to construct, and they are very highly resistant to rust, and they have the features like antimicrobial properties, and these are makes polymers more suitable biomaterial for many of the applications. But they have some few limitations, like they have less vigor and variation in shape, as they are easily deformable. We can say when it comes a pressure, they can change their shape or they can move away from the or they change shape according to the stress or pressure applied to them, and they have chance of high chance for the degradation, easily degradable because they have the changing variation in the shape. So usually polymers we are applying in contact lens sockets, heart valves, blood vessels, artificial hearts, hip joint, etc. Are the applications of these polymer-based biomaterials. And the last fourth group, what we are talking about here, is nothing but the composites. We can call them also as biocomposites. So they are physically wonderful or powerful materials because they have the properties of metals, ceramics, polymers, etc. combined together to form a new group of materials. So they have enough resistance to rust and wear, and they are eco-friendly to living tissue. So the major requirement or limitation is there in homogeneity. It is not easy to make a homogeneous sample as compared to the other three group of the biomaterials, and they are not easy to construct also. These are mainly used in joint replacement, bond cement, and dental implants. So, in short, if we talk about the major characteristic of biomaterials, we can say every biomaterial should have outstanding biocompatibility, then only we can use it in vivo applications, and they should have sufficient mechanical properties so that we can use them for load-bearing applications or load-bearing implants, and they also should have high quality physical and chemical properties. So like when we are talking about small biomaterials, they should their conductivity, their morphology, their chemical properties, everything are quite important in order to use them for some medical sensing applications, and also they should have enough resistance to wear. So when we talk about a hip or joint replacement or a hip replacement implant, or in that case the most of the part of the body's weight will be handled by this certain implant. So this can also our patients, the person who is using the implant, depending upon the lifestyle and activity, it can go more here and here. So if we are using a biomaterial in such applications, there should be that material should have enough resistance to wear and enough resistance to rust also, because our body is mainly consisting of lot of body fluids like blood, lymph, everything. So all this lymphatic system or cardiovascular system will be continuously flushing our body fluids throughout our body. So when it will come in contact with this implant material, it should not create much reactions and cause the material to rust. Because when it will start rusting, or when the rusting has started, ultimately the life of the implant will vary, or it will get shortened, and it may get uh, they break according to the condition. So those are things to be taken care when we say about this characteristic, like it should have enough resistance to rust. And also integration for bond implant. So when we are using a stainless steel based rod or a titanium alloy based rods for different applications related to the bones or our spine or backbones or femur, so those cases we require materials which are also integration. So it should work in connection with the bones as a part of the bone, and it should not treat or bond should not treat this particular material as a foreign object and create some issues like cracks in the bonds, or osteoporosis should not happen. So all those things should be taken care. So that's why we say osseous integration is an important characteristics for any biomaterial which is used for bone implants. So, considering all these properties, characteristics, when we are going to design any biomaterial based system, we have certain design considerations. Like we see check for the bulk and surface properties of the biomaterials. Because they control the dynamic interactions that takes place at the tissue and the implant interface. So we need to know in bulk how the material will behave, or what are the surface properties, if it is a rough or it's a uniform one, or is it a more reactive surface, or it's an inert surface. So all these things has to be considered when we are deciding a tissue implant, joint or interface. And these characteristics and the changes in the characteristic that may take place over in time in vivo should be known for designing biomaterial for specific applications. We may test the materials in bulk and surface outside or in a laboratory condition. That may not be true when we will implant these particular materials in vivo in our body, because our body fluids, we don't have any like buffer solutions or materials which can mimic our body fluids exactly. And person to person, the alkalinity or the pH values of the body fluids may vary slightly. So all these things should be considered when we are designing a biomaterial based device for using in our body. And so because we say cardiovascular implant, so blood will be continuously in touch with that particular implant. So on all the characteristics, or blood is a very complex biofluid which contains sodium ions, potassium ions, hormones, or blood cells, and we also have content of water. We also have the other acidic and alkaline contents which will be caused by the inhaling and exhaling of our body. So all these things continuously coming in contact with any cardiovascular implant can create or cause some reactions, and it can even make the implant to fail. So these all should be considered when we are designing the biomaterial based implant. And also it's important that where we are going to use this implant, whether it is in the heart, whether it is in the hip, or it will be work in connection with a bone, or whether it will be using in for supporting spine, or we will be using it for any surgery applications, or if it is in the eyes. So which part of the body we are using it, based on that also we have to modify or consider we have to decide the design considerations. So when we say we want to generate or we want to synthesize the biomaterials, so we look for the whatever monomers or whatever the materials we are using for making the biomaterials. We check their biological characteristic, their chemical characteristics, their physical characteristic, and their mechanical characteristics. So a material with all these characteristics are suitable for making any substances, or we can say any new biomaterial which we want to use it for certain applications. So we have to see their biological properties, mechanical, physical, and chemical properties. So when we talk about the performance of this biomaterial, so when any biomaterial which we are using in the body, the success of these biomaterials depend on factors such as their material properties, and what design we are using for the implant, and the technique used by the surgeon, and health and condition of the patient, and the patient activities. So material properties, as I told you, we are using a polymer based material for a load bearing implant. We know that the polymers cannot support or cannot bear a high load, so automatically it fails the. So which area we are, or what kind of implant we are designing, depending upon that we have to see the material properties. And when we talk about an eye intraocular lens, so when we design such a lens for our eye using a biomaterial, we need a flexible material. We cannot go for a ceramic or a metal based material to design an eye lens. So all these things properties have to be taken care of. Material properties have to be analyzed properly before we are going to design or think about any biomaterial based implant or a biomaterial based system. And design of the implants also is important. The shape, the structure, the stress and strain handling capability, the resilience of the material. So all things should be taken care. Then biocompatibility of the material. We cannot use any material which are not biocompatible at all. Only biocompatible materials can be used for in vivo applications. And also the technique used by the surgeon also matters. So whether it is for a surgery, whether it is for an implant, so what kind of other techniques are being used for this particular, along with this biomaterial, that is also important. And health and condition of the patient also important, and for because the body is a very complex biological system which contains lot of elements, lot of fluids which are different pH, different materials. So all these come, when it will come and contact with certain material, it can react and it can cause some infections and inflammations in the body. So health condition of the patient and the patient activities are also important. Because more implant with a patient with a highly locomotive activities will have more and more, can cause more tear and wear to the implant. So when we say all these things, so if we know biomaterials, if we have certain properties, how do we, what do we apply usually these biomaterials? So based on the problem area, we will have certain biomaterial applications. So something like, you can say, substitution of a damaged part. So we have a kidney dialysis machine or a hip joint. Somebody has a broken hip joint or a osteoporosis affected the hip joint and you want to completely change the hip joint. So in that cases, we can go for a biomaterial. And in cases like supporting healing, so like bone fractures, in that cases we can support them with bone plates, screws and sutures, and also it's help in prophylaxis. So where we need catheters and drains, and helps in analysis, like we need catheters and probes, like we do body or diagnostic, many of the diagnostic instruments where we require, which we use to check the body parameters, we want to find out the electrical parameters or any physiological parameters. So then we have to use for catheters and probes, which are mainly made up of biocompatible materials. And also for some cosmetic problems like plastic surgeries or a mammoplasty or a chin augmentation, we can go for biomaterials. Then some functional defect, like we have a Harrington spinal cord is an example for that. Some people will have the cord or the bended spinal backbone region, which may affect the functioning of their spinal cord. In that, the backbone correction will be done with the help of Harrington spinal rod. And sometimes we want to improve function of any of our body parts. So like or any organs like heart, which cannot create enough cardiac output. In that case, we add cardiac pacemakers. And if you have visual problems where we want to create contact lenses using biomaterials. So in order to improve the function of heart or eyes, we go for biomaterial based cardiac pacemakers or contact lenses. Also based on what organ is facing the problem. So based on that also we can use the biomaterials for, suppose if we have any issues with the heart, we can have biomaterial based cardiac pacemaker, artificial heart valve, total artificial heart oxygenator machine, artificial heart, etc. And in the case of lung, we can have an oxygenator machine which is completely based on biomaterials. For eyes, we make contact lens, intraocular lens. Then for ear, we make some cochlear implants, which can even work with BCIs, so that we can have help in aid in the poor auditory functioning of the ear. Then also related to bone, we will have bone plates and screws to support the fractured bone. And we have kidney dialysis machines made up of biomaterials, or we can also use catheters and stent for the support of urinary bladder system. So we, before going into biomaterial compatibility or other part, we'll see some of the examples which will attract you into the field of biomaterials, so that we'll think about why don't we design some system using some of the materials like this. So nowadays, I will be discussing about some of the applications which are used by biomaterials. So intraocular lenses are such an application which is mainly used to aid our eyes, people with glaucoma or vision issues. So usually we use polymethyl methacrylate or PMMA, in short we call that, or acrylic based materials or silicons for making the intraocular lens. So the major challenge in designing an intraocular lens is nothing but the long-term biocompatibility with optical properties. So your eyes also have some fluids, and also this should work in coordination with the other parts in the eye. So long-term biocompatibility is expected to have for these materials which are like PMMA or silicon to design an intraocular lens. Next one is vascular grafts. So vascular grafts are mainly designed to support our cardiovascular system or the arteries or veins, where we have some problems like, as I told you, aneurysm, just something like, or we have some vascular issues like what is it, varicose issues. So all those cases, if you want to replace some part, or if you want to cover up the aneurystic arteries or veins so that it should not bulge more, so we go for some vascular grafts. So usually we use polyurethane and Teflon and Dacron as the material for preparing vascular grafts. And the major issue in the case of challenge in the case of any vascular grafting is the maintenance of mechanical integrity along with the natural body arteries or veins. And also we need long-term biocompatibility so that it should not cause any clotting of the blood cells or blood in the vascular grafts. And if such things will happen, it can even affect the well functioning of the body. So we need materials which are using for vascular grafts should have a long-term biocompatibility. We should be able to use it for years in our body before, because it will not be feasible to keep on changing the vascular graft every year, 1 year or 2 year. So we look for a long-term biocompatibility so that we can give a long life to the grafts which have been implanted in the body. So you can see here, these are some of the nanomaterial based grafts which have been used nowadays for made up of Teflon, used for nowadays for using as a vascular graft. So we have artificial hip joints. So artificial hip joints are basically used to support the broken hip or an osteo or damaged hip in any human body. So we use stainless steel, titanium and its alloys, or ultra high heavy high molecular weight polyethylene or UHMWP kind of materials for making the artificial hip joint. So you can see this will be the structure. It will have the since we have a ball and socket joint at the hip, so the joint portion will be like this, and which will be having a polyethylene layer, and we'll have a femur head covered with all this liner, so that it will have less friction inside the joint, and we'll have the hip implant. So this portion is the hip implant, which is generally made up of stainless steel, titanium, and also along with HMWP linings. So the major issue in the case of artificial hip joints are prevention of wear, loosening of overextended periods. So at least we should provide a lifetime of around 10 to 15 years when we are using such joints. And also we use materials, carbon and metal-based materials used for making hot walls using biomaterials. So mechanical walls, you can see using carbon and metal-based mechanical walls are used nowadays. So we also use biological or bioprosthetic walls, which are usually made from pig or tissue, sometimes from human tissue also, in which case they call them as, if you are taking it from the human, we call them as homograft walls, and it can be treated to make sure it is not projected by the body. So our own body, if it is used, so we can achieve maximum biocompatibility and use it in the body without any further issue. So like this is an example for our Indian-made heart valve using the biomaterial. So we call that's the Chitra valve, which has been contributed or which has been designed and implemented by Sri Chitrathirunal Medical College from Kerala. And so you can see it is made up of an alloy and a polymer based material. You can see here the frame is made up of a LMS 25 alloy, and the disc is made up of a ultra high molecular weight polyethylene, and we also have a polyethylene terephthalate or polyester based sewing ring which can be sewed into the heart and which can be used for helping the people who are having a failure of their valves or non-functioning valves can be replaced using this Chitra valve. So the main important feature of this valve is nothing but soft closing around by and the virtue of a plastic occluder. So as I told you, this has been mounted around more than 115,000 times per day in a normal person. That is usually we have usually in this Chitra will be flutter more than 115,000 times per day in a normal person having 70 to 80 heartbeats per minute, and this translates the disc opening and closing 40 million times in a year on average. So this can cause a high amount of strain on the material. So the material used should be extremely durable in terms of its wear and tear. And also, the biocompatibility, tissue compatibility and blood compatibility of the material is also a major requirement when we design a heart valve using a biomaterial. So, that's why we go for ultra high voltage.
ಇದು ಮಾಡ್ಬಿಟ್ಟು ಹೋಗುವೆ ಅವ್ರ ರೂಮ್ಗೆ.
Has everyone used this? Sorry. Such as durability, longevity, high stress resistance, wear resistance, tissue and blood compatibility, fatigue strength, and toughness. So we can have these heart valves using biomaterials in lot of ways. So we have injection molded heart valves, additive manufactured heart valves, fiber reinforced heart valves. So these are some of the commonly used techniques for making heart valves using biomimetic or biomaterials. So also we have used some ventricular assist devices. So not only for valves, we also support the ventricular functioning of the heart using some biomaterials so that whenever enough cardiac output is not able to produce by the human body, these kind of devices can help the heart to pump the enough cardiac output and give an increased lifetime to the person who is suffering from such an issue. So this is we can consider as a half of a total artificial heart kind of thing, this ventricular assist devices, and this is like it's a result of a long-term experiment and a life-prolonging tool. So they are now used to maintain patient with a failing heart while waiting for a heart transplantation. So if any issues is there, if you are having a VAD, we can support them with biomaterial-based VADs can be used to support such cases. And the important issues with this ventricular assist devices are to maintain a proper electromechanical functioning and also the prevention of infection and clotting of the blood. So if the material has to be biocompatible and the material, whatever we are using along with this VAD should have the proper electromechanical functioning. So till now you keep on saying it should be biocompatible, material should be biocompatible. So now we can discuss what is biocompatibility. So biocompatibility is the ability of the material to perform with an appropriate host response in a specific application. So it's what's a book written definition for biocompatibility. So there comes in words, what is this appropriate host response? That is, when we are installing such a material, using such a material in our body, the material should have some resistance to blood clotting. When we are using a hemodialysis machine, biomaterial is used in a hemodialysis machine, and this patient's blood will come in contact for around 3 to 4 hours. So during that time, if there is any reaction will happen, the blood will get clotted. It can even cause the death of the patient. So one major issue what we consider is always is the resistance to blood clotting. Another one is resistant to bacterial colonization. That is, we are using a urinary catheter. It may be inserted in a week or for a hip joint replacement process, maybe for a lifetime of the patient. So if there is any infection comes that can spread to the remaining part of the body and it can cause death of the patient. So we should check for even resistance of bacterial colonization. And we also see like it should have a normal uncomplicated healing. So tissue engineering, when we are implanting it and when you use it for a long time, it should not create the wounds or complex wounds or any other issues in the body. So these are all the things when we check when there is a when we say a material has to be biocompatible. So usually biocompatibility characteristic involves the acceptance of an artificial implant by the surrounding tissues and by the body as a whole. So if you are using a steel plate to support the bone, fractured bone, that material should not be treated as a foreign object by the body. It has to be completely accepted as a part of the body by the surrounding tissues as well as our whole body. So we choose some biocompatible materials that we use which do not irritate the surrounding structures, which do not provoke abnormal inflammatory response, which do not incite allergic or immunologic reactions, and also which it is not to be a carcinogenic materials. That is, when we these are the major criteria when we see the concept of biocompatibility in a biomaterial. So biocompatible materials should have adequate mechanical properties and should also have appropriate optical properties, and they should have an appropriate density. So these all properties we will look in the case of when we design a material, when we synthesize a particular biomaterial for a new biomedical application. So, so when we are devising any medical device development process, first we will see the selection of a suitable biocompatible material. So these are essential step because the types of tests required for evaluation of a device depending upon the physical and chemical nature of the materials, in addition to the nature of device exposure to the body. So maybe we see a material. It may appear suitable based on its physical properties, cost, or availability, but might contain some toxic chemical components. We can say Teflon. Teflon is generally we say it is inert, but when we use it in the body. So when there is a case study, so it says that when used for a knee implant, this has caused a further inflammation in the knee, and it has been caused a further infection in the body, and direct use of Teflon has been was the reason for the inflammation that happened at the knee implant. So we cannot, even though we see like they are inert or they are quite have good properties, physical or chemical properties outside the body, that doesn't ensure that these materials can be used directly into the body. So therefore, we always screen such materials at an early stage to eliminate that toxic, whether they are toxic or they are sufficiently biocompatible or non-toxic for the intended application. The chemical constituents and potential extractables should be identified and quantified for overall safety and assessment of the device. So we do a lot of tests. We find out the potential toxicity of the material so that which can be used inside the body. So the device material should not either directly through the release of their material constituents into the body, which can produce adverse or local systematic effect, or be carcinogenic, or produce adverse reproductive and developmental defects in the body. So these all criteria will be taken care when we do the biocompatibility testing. Therefore, evaluation of any new device intended for human use requires data from systematic testing to ensure that benefits provided by the final product will exceed any potential risk proposed by this device material. So usually when we do biocompatibility testing, so when we synthesize a material, so that this can be used for such an implant application, or it can be used for an eye lens application, or so on, etc. So we basically the material will undergo biocompatibility testing, and the procedure for the biocompatibility testing include cytotoxicity, acute subchronic and chronic toxicity, irritation to the skin, eyes, or umbilical surfaces. We check. We check for their sensitization. We also check for hemocompatibility. And we also see short-term implantation effects. For a short-term period, if it is implanted in the body, how it will react. And we check for genotoxicity. And finally, carcinogenicity and its effects on reproduction, including the developmental effects. So these all tests will be done to ensure that this particular material is a biocompatible material. So we when we do that biocompatibility testing, so we check for these questions.
ನೀನು ಏನು ಆ ಕಡೆನೂ ಕಾಲು ಈ ಕಡೆನೂ ಕಾಲು.
Excuse me, ma'am. So we check for whether how to characterize the material that will be processed into a medical device or implant. We also check how these biomaterials can be evaluated to determine if they are biocompatible, and also how biomaterials can be evaluated to determine whether they function appropriately in the in vivo environment. As I told earlier, we see in vitro or outside the body, it can have a lot of functionalities, but we cannot expect the same properties to be resulted or the same properties to be obtained inside the body too. Since our body is a very complex biological, physical, physiochemical system. So these are the procedure when we do the follow when we do a biocompatibility testing. So when we do the step one will be the development of an implant material and its characterization. We synthesize in the R&D works. We synthesize the new biomaterial, and synthesized biomaterials will be characterized for its basic characteristics. Like whatever it is a conducting application or a sensing application, we do electrical characterization. Also, we for other applications, we also check with surface morphology, its structural characterization, functional characterization, electrical, all these characterization we will do, and then step two, we give it for the in vitro testing. That is outside the body or effect on the individual cells, how this material will affect the particular cells, whether we check for the cytotoxicity as well as the genotoxicity. Once that is done, then if it is a failure, then we have to go back and re-synthesize the material with the appropriate properties. If it's a success, we go to the step 3 where we do the in vivo implantation in animals like monkeys or dogs or mouses. The animal model we will use in the step 3 after the in vitro testing. So here we will check for the tissue viability, the histology. We also check the inflammatory cytokines and toxicity studies of nano-sized vertebrae. So all these things we will check in the animal model where we do the in vivo implantation. Once this is successful, then we will check for the clinical feasibility and clinical efficacy by doing by human trials. So I can say from bedside to bedside, we will be shifting the material so that whether it can be introduced in the body with human trials. So it's not a one-step process. It will be when we synthesize the material, we do in vitro, we do in vivo testing. Then after, once it will pass all these tests, we check for the human trials for clinical efficacy and clinical feasibility, and then it can be go to the product stage, or it can be used for wide usage of the implant material can be done after all these tests. So usually testing of biomaterials has 4 phases. First one will be the raw material and screening, characterization and screening, where we do the chemical, physical and biological characterization. Then we check for the material biocompatibility, where we do the cytotoxicity, that is check whether this particular material is harmful to the individual cells or what. Then we check for sensitization, is it producing any anti-allergic effects or irritation or systemic toxicity or chemocompatibility, is it compatible to be long-term usage with blood or what, and its carcinogenity. All these biocompatibility testing will be done at the material biocompatibility testing stage. Then we'll go for the product and process validation, where we check for the environmental effects, the manufacturing problems, the sterility of the finished product, and the final testing and qualification. After all these things, we go to the routine testing, where we do the periodic audit testing, and finally the release testing will be done to the these all things will be done to the complete the routine testing, and that product will be introduced into the market. So toxic materials kill cells by inhibition of key metabolic pathways. So we check for all these things, and we also see for the source of toxic materials, whether it is extractable or whether whatever additives you are used during the manufacturing process or plasticizers or monomers, whichever the material which is causing this particular killing of the cells or cytotoxicity, that we will be analyzed, and potentially depending upon the dose of chemical delivered to the cell. So we have an exposure dose that is applied to the system, and also delivered dose is nothing but the dose absorbed by the cell. So how much dose we are giving into that particular cytotoxicity test system, and how much is being absorbed, and based on all these things we come up with a report that what is the key factor that is being creating issue, or that is being the causing the failure of the system or this material in any when we are using in a human body. So we basically we can classify biocompatibility test into two phases. As I told, was in vitro, which is a rapid, inexpensive method, but it does a poor representation of the physiological condition because it's completely outside the body. But it is considered to be the first step of any biocompatibility testing. Another one, we have a better approximation to human environment by using any animal model, because we through Animal Welfare Act or demanding protocols will be using these in the testing animals, and finally right animal model approximation to the human environment will be chosen, and this is in vivo testing is considered to be the second step prior to the clinical use. So in vitro testing, so you can see we use the cell cultures, we dissect the tissue, finally chop it, free the cells from the extracellular matrix via some digestion using trypsin or collagenase, then place them in a dish with nutrients and keep them warm. So something like we add the material into that and we check for using the cell cultures in the case of in vitro testing. And also we use some assay methods in the case of in vitro testing, like direct contact. So we in the cell culture we directly apply the biomaterial and we check how it is whether it is toxic to the cells, or is it okay with the cells, or is the cells are being alive for a longer duration or what, in the direct contact method. And then agar diffusion, we use agar sheets through which we will do a controlled delivery of the material, and also we have a method called as elution. So we will see direct method. So contact method, we use a monolayer confluent cell culture, which we usually use a mouse fibroblast are used as the basic cell material for the direct contact experiments, and this will be done for a duration of 24 hours at 37 degrees Celsius. And these cells in contact with these biomaterials, it can change their morphology or may die or lose adherence to the dish. So all these things will be checked in the case of a direct contact technique of in vitro testing. So we can see, like we check a hematocyanin blue stains, that indicates that using a staining method we can check whether the stains leave adherence to the cells, or whether the toxicity, that is whether they are dead or alive. All those things we can check in the case of a direct contact method. So we use a L929 mouse fibroblast. Why? Because it is easy to maintain. It has a good correlation with animal test, and fibroblasts are present in the wound healing, where when we use any cut or wounds, the wounds will be joined by using the formation of fibroblasts. So that's why we use these mouse fibroblasts for the testing of this direct contact method, testing of the biomaterials for their biocompatibility. So, and also you can see down here an example of direct contact method. So, confluent monolayer of you can see is a magnification of 100 of L929 mouse fibroblast cells exhibiting cell-to-cell contact. So you can see here how they have been distributed, and the appearance is indicating of it's a non-cytotoxic or a negative response. While in the case of, you can see the material applicated, this second sample, which shows a positive cytotoxic reaction, so which has killed the, it is done using an elution method, and these cells are grainy and lack the normal cytoplasmic space, and there are considerable open spaces in between the cells, indicating that a lot of cell lysis or disintegration has been occurred in the particular sample. So this indicates a positive result. A negative response indicates that the material is positive biocompatible, and a positive cytotoxic reaction indicates that that material is a non-biocompatible material, or it's not suitable to use along with the body tissues or cells. So when we come to in vitro testing, we have another method which we call as the agar diffusion method. So we use a cells, whatever the fibroblast or the basic cells, whatever the extracted cells will be used in the particular testing, and above that we'll use an agar layer, and or above the agar layer we will be keeping the biomaterial for the in vitro testing. And the agar is nothing but it's a gel-like polymer derived from the red alga, which has a controlled diffusion, or it allows a controlled diffusion of the materials through this. So the chemicals will diffuse through this agar layer, and we use specific stains to label the healthy and unhealthy cells. So you can see the green color sample here, which indicates that which has not got any or dead cells or the areola region around the cells. That indicates that it has high resistance towards these biomaterials, or this biomaterial will not harm these kind of cells. So normal, also you can see here, inhibiting areola formed in the other three samples, indicating that they are very sensitive to these biomaterials, so they can have an adverse effect if we are using these biomaterials in the along with this kind of cells. So a larger or a wider areola indicates that it has a high sensitivity compared to other two. So this is another example. So you can see some of the agar diffusion method. So here you can observe an areola here near the sample, and this sample doesn't have any areola or an like this one. So this indicates that the immunity of the cells towards that biomaterial, or the biomaterial harmfulness of that particular biomaterial. And the last method of in vitro testing is elution. So elution, we prepare the extract of that particular biomaterial, and that can usually we do in by mixing it with oil or water-based solution, and these materials will reach into the solution, and then it will be applied to this solution will be directly applied to the cell culture, and then we will do the similar stain-based viability testing to find out whether the areola is formed or what. Based on that, we can tell the compatibility or biocompatibility of this particular material. So these all methods have their own advantages and disadvantages. So usually direct contact is the like what say as the advantage of eliminating extraction and preparation of diffusion, and it also can create a target cell contact directly with the material, not in an indirect way. So, and which will direct contact method also mimic the physiological conditions, and the exposure time by adding we can extend the exposure time by adding fresh media into that particular method. And agar diffusion is the what is it? Can eliminate extraction preparation method of the sample, and which has a better concentration gradient of toxicant. So all those things are the advantages of agar diffusion. And when it comes to elution, so it is a separate extraction from testing, and we have a dose response effect. We can see for how much dose, what is the effect in the case of an elution method, and but it requires an extended exposure time. So the disadvantage with the method is that if there is any movement of the sample holder, then direct contact method can create any can generate cellular trauma, or it can also the cellular trauma can happen with high density materials. And agar diffusion always, since it is a layer method, so it requires a flat surface, and it has a limited exposure time, and sometimes we have the chances that the cells can absorb water from the agar, and which can alter the results of the testing. And elution, it requires a lot of time, and it has a complicated steps. So in vivo testing, so these are the methods. So direct agar method and elution are the in vitro methods. Now we have in vivo testing for the biocompatibility. So in vivo testing are critical for the development of any clinical devices. Without in vivo, we cannot testing. We cannot use any of these materials in our body. So in vitro test cannot replace in vivo test because in vitro is completely outside atmosphere, different conditions. It's only in a laboratory experiment we do the in vitro test, and we'll not get any idea about the inflammation, immune response, or single cell reaction or tissue remodeling in the case of an in vitro test. So we need in vivo test only to find out all these problems. And in vivo test provide interactions of different cell types, so how they will react and how what will be the result of this particular reaction, and the hormones present in the body, how can it affect the working of this biomaterial based device, then interaction with the extracellular matrix and interaction with blood bone cells or proteins and molecules can be studied only if you conduct an in vivo testing of a biomaterial. So implant effects can be simulated in vivo. So you can see one here. So so if you are not properly designing, so the shielding effect cannot be calculated if you won't do an in vivo testing. So this is a post-operative image, and after certain years of using the same implant in the body, how it has caused osteolysis, and the bones around the material has been damaged, and the total damage to the bone has happened due to the osteolysis caused by the implant material. So these all things can be assessed only if you do an in vivo short-term or an in vivo testing. So these can in vivo testing or the simulator in vivo can provide dead space created by the implant, then insoluble particulate material released by the implant, interaction of biological factors within the implant, mechanical loading experienced by the device. So all these things has to be simulated and studied then before using the material as an implant in the body. So these parameters will get from the in vivo testing. Also, we use animal model. So after the simulation, we use it in the animals to find out the animal model can give much more details about the material. That is, it can approximate the size of human bone. So some canine model we can use where we can use the same size of human bone. We'll get the size and length of the bone same as the human body, and we can install it in that particular animal and see whether the same effects will come, whatever the effects happening, and based on that we can judge what will be the effect when we use the material in our body. The drill holes in diaphysis, that is cortical or metaphysis of femur or tibia. Then implant devices in the holes, assess the integration of implant, assess the tissue response. So how we do in the canine model is nothing but select the bone, which is very similar to the human body. We do the holes, drill some holes in the femur or tibia part of the leg, and implant this biomaterial device in those holes. And based on that, we calculate the osseointegration or osseolysis of the implant caused by the implant, and also the tissue response. This is the musculoskeletal model of method of testing, which is done by using animal model. So also we have in vivo testing using with respect to connective tissue. So connective tissue, we check it in the dermal region. So cutaneous or subcutaneous sites on the skin will be chosen to assess the biocompatibility, which is readily accessible. So we can thickness of the fiber capsule measure the biocompatibility. These kind of experiments are done directly by using guinea pigs and all. And also in vivo testing of muscles. So paravertebrate muscles of rats, rabbits, and dogs are used to detect the toxic leach. That is how slowly the toxicity will spread from the biomaterial molecules into the body. Will be studied with the help of animal models using rats, rabbits, and dogs. And the thickness of fiber as encapsulation measure will give you the measure of the biocompatibility. And we do immuno testing for vascular applications. So blood compatibility of materials used as vascular prosthesis will be analyzed in this. So use of replacement segments of patches. Then carotid or tubular vein or familiar or anterior venous are selected for this kind of testing, and the response varies between different species. So person to person, the response will vary, and this is used for vascular grafts, which we decide using the biomaterials. So these are the major standards we are used in biomaterial testing. So each standard defines what kind of selection of test to be done for that particular grade materials. So this is completely done by the International Organization of Standardization ISO along with FDA for setting up the documents for giving the guidelines of biomaterial testing. So we have guidelines on selection of test, animal welfare requirement tests for genotoxicity, carcinogenity, reproductive toxicity, etc., etc. So all these biocompatibility testing should be done according to the standard, and the ethical clearance should be issued based on the standards which has been mentioned in the document. Then only we can further proceed those with the production and development of devices using these kind of biomaterials. So some example we can see, so we can see the ISO 1099310, which is a standard for calculating the sensitization of biomaterial. So this we check for the sensitization to latex glove after use of several weeks or months. So this has to be passed under this standard before using it on the hand. Otherwise, the issues or the sensitization issues may result, and which can cause harmfulness to the skin and to the person who is using it. So the biomaterial testing standard should check this kind of sensitization before using it in the body. Now, another one example is ISO 1099310, which is for sensitization using the positive responsive to maximization test in a guinea pig. So we apply the material for in a subcutaneous level for a certain period, and we observe for the variation in its that particular region where we apply the material, and if there is any variation, discoloration or the swelling or inflammation, which can indicates that this is not a compatible material, and this has to be undergone should be done under this particular standardization, and only negative sensitization can give a positive biocompatibility result. So standards also we use 109936 for implant effect. So we do a short-term implant of the particular biomaterial implant in the body, and we check for the nearby cells, how they react to that particular implant. So you can see here there is no much damage to this is the material implanted, and the nearby tissues are not much damaged. That means it's a minimal response, which indicates that this implant can only cause a minimal damage to the nearby tissue, so which can be a positive towards its biocompatibility. While the other material which will have been used, you can see a severe response will look like this. That is, the nearby tissues will be damaged, or the cells will be completely damaged, which can cause an inflammation and further continuous damage to the nearby tissues and bones. And such material will not be passed under the compatibility test, and which will not be considered as suitable for making the biomedical bone or replacement implants. So at last, when it will come to biocompatibility, we have to discuss about two important criteria. One is carcinogenicity and the genotoxicity. So when we are using any implant for a long-term usage in our body, the carcinogenicity studies has to be done to observe, and that is whether the animals it will be done on animals or a major portion of their lifespan to detect any development of neoplastic lesions, or we can say some tumor formations during or after exposure to various doses of a substance. So usually this is conducted with oral dosing. So for implants and medical devices, only extracts can be tested, as that may be administered intravenously, and this will necessitate certain modifications of the standard procedure. So only for very few products we have this particular test can be justified. Okay, so usually this is done in mice or rats dosed every day for 18 to 24 months. So this continuously, this particular material will be dosed given to a single dose or double dose to the particular rats, and this will be observed. That's what we can say, whether it is inducing any tumors in its body or inducing any adverse effects in the body for a long-term usage. So usually for medical devices, we use only one dose one dose level to this one. But at the completion of the dosing period, we see all surviving animals are sacrificed and their organs or tissues are examined microscopically for the presence of tumors. So we do for 18 to 24 months for a single dose of this particular medical device material, and then we check for they will be sacrificed. They will check for the tumors or presence of other carcinogenic things in their body using a biopsy. So, an increased incidence of one or more category of tumors in the dosed group would indicate that the product tested has potential to induce tumors and could be considered as a possible carcinogen in humans. So, that particular material's biocompatibility fails there, which cannot be further used in vivo in our human body. So, this is the how we do the carcinogenicity test in the case of a biocompatibility testing of a biomaterial. Another one we check for is nothing but genetic toxicity. So genetic toxicity tests are used to investigate materials for possible mutation effects, that is damage to the body's genes or chromosomes. So usually in any organism, there we have the smallest unit of independent existence is of course our cell, and each cell has contained to maintain or sustain our life. We have genes and sections of DNA devoted to specific function. And these all are considered, and DNAs are made up of chromosomes, this all we know. So these alternation in any part of this DNA structure will result in a permanent and inheritable change in the cell function called mutation, and that agents can cause mutations are known as genotoxic agents or genotoxins. So it will be not only to that person, the coming generations from their family can also get affected by the usage of such biomaterial based devices, implants in their body. So the genotoxicity has to be analyzed before we implant any material in a human body. So mutation formation content of genetic material is propagated through subsequent generation of cells. So usually we do gene mutations or chromosomal mutations will be studied, and this will be any alterations or chromosomal or morphological alteration in the sample indicates that this material will cause a genotoxicity and which cannot be further reversed back, or it can be inherited to the other people also. So that's why that material will not pass the biocompatibility test if it shows a positivity for a genotoxicity. So based on all these things, so these are the basic idea about all the biomaterials, their types, their properties, their characteristics, and the important aspect in the biomaterial is the biocompatibility, which we do using in vivo and in vitro test. And so when we talk about the biomaterials and their research areas, so usually our research team is mainly working on disease detection and drug delivery applications in the area of using biomaterials, while there are lot of areas which we can explore using biomaterials, which include the drug discovery, disease detection, environmental monitoring, soil quality monitoring, food quality monitoring, toxins of defense interest, water quality management, prosthetic devices, etc. And the bigger and the major area, nothing but the biosensors. So these are the relevant areas of research when we talk about biosensors, and we work in the area of mainly biosensors for disease detection and also biomaterials for drug delivery, for cancer applications, as well as for some very relevant pandemic diseases also. So these are our research areas. Okay. So further in depth of the characterization of the sensing material and the other methods what we will be using for characterization will be discussed in the characterization session, which will be coming in the tomorrow, day after tomorrow. So that's all for today from my side. If you have any queries, you can ask me. So thank you so much, Jalija ma'am and the whole team and BIT College for providing us such an opportunity to talk on biomaterials.
If you have any queries,
Yeah.
you
Yeah,
can
please,
ask us.
if you have any questions,
Any questions?
Madam, as an electronics engineer, can you propose any research area in the stream?
yeah, see, being an electronics engineer, I work in this field, so there are lot of opportunities. I told we work on biosensors for disease detection. So we even designed our own malaria sensor, which we are using as a blood sensor to detect malaria from malaria biomarkers from the blood. So as an electronics engineer, the area of sensing is widely open in the using biosensors, which can be used for a disease detection, which can be for any other body parameter detection, all those things. So sensors are there, they even design even medical devices which are compatible, portable, non-invasive. So there are many of the methods which we are nowadays using the medical devices, mainly which depending upon measurement from blood, or there are a lot of invasive methods which we can replace in a non-invasive way, and we can design our own systems where we can employ these biomaterials or synthesis, create our own biomaterials and help the society in those ways. Yeah. Any other questions?
Okay.
Hello.
If there are
Yeah.
no questions, okay. Okay, sir.
Hello, madam.
Yes, sir, please.
Madam, this interventional cardiology,
Yeah.
while you are doing angiogram, madam, that wire is there now.
Yeah.
How much nanometer wire, madam, that is thickness?
So the whatever we use, so the conventional techniques, whatever we use, we cannot tell how nanometer this all those things and all. So depending upon the applications, we design specific material or the instruments or the different catheters which will be suitable for that particular person's this one. So usually few nanometers you can say. So less than 100 nanometer will be using those things. But even designing such systems in those nanometer levels are not, it's not that easy. So it will be completely, I can say it's an application specific thing. So precise applications, we develop precise equipment, even processes also, when we say an implant or a very joint implant or a hip implant, from person to person it will vary. The size of the joint, the length of the bone, so everything. So this will be prepared precisely suitable for that certain patient or a person.
Okay, madam. Nowadays, as per the orthopedics, they are giving the biomaterials, which is not
Yeah.
necessary to remove again. In that
Yeah.
same question, is there any coronary arteries? Like at present, we are using stents, whatever coronary.
Yeah.
That is okay. But
So
what we are
mainly
making
nickel
imagine,
or nickel titanium alloys are used for staining stainings and related these things, transplants or usage of angiograms or those things. So still there are a lot of memory foam alloys or memory based alloys which can reshape and come back to the normal. Such researches are going on that area also, sir.
okay, okay. Actually, this whenever this arteries is there, madam, 3.5 mm to 2.21 mm is there.
Yeah.
The stents.
Yeah.
But stent in CAD lab, while we are talking with doctors, what they are telling, that length should be more, because whenever they are going 2 or 3 clots in heart,
Yeah.
to covering the 2-3 clots with one stent, they are asking for long stents.
Yeah.
Is it possible to make madam long stents?
Yes, such things are available also, sir. Such products are also being used in the surgeries. So which are very, that's what I told, memory, like memory foam alloys, like memory shaped alloys, that is, they very small size, then when they will insert it into the arteries, which will expand and it will remove the blocks and it will again come back to its normal shape. Such things are also designed. So there, I hope such products, if you Google it, you will get so many products related to that. We basically work on polymer nanocomposites and polymer-based sensors for room temperature sensing of various disease biomarkers and cancer detection applications.
Okay. Madam, is it the same case for in nephrology?
Yeah. Pardon?
Nephrology.
Uh-huh.
Okay, okay, madam. Thank. Whatever it is, finally we are facing the problem in this biomaterials, madam.
Really, it's not easy to generate a biomaterial which is, as I told, a biocompatibility issues.
Yes, madam.
Genotoxicity. One more, only one phase it phase, we cannot put that one into body. So because and person to person, the lot of criteria will vary. The blood, the genes, everything will vary. So all these things, how may be suitable for one person may not be suitable for the other person. So there are a lot of complexity involved in the implementation of the biomaterials. But still, thanks to the technology, we are able to design so many materials like titanium or platinum-based inert materials, which we can directly use in our body for at least for 10 to 15 years, not for the whole lifetime.
Yes, madam. One more question, madam. Recently, we go through one case in orthopedic.
Okay.
For steel rods, they are asking 20,000, which is for bio, whatever it is, the materials, non-removable steel rods. They are asking 75,000, madam. Is it that much cost?
The production, that's a problem with the steel. Steel, like the production cost, material is okay, but it is not all those things. But the complete production and manufacturing cost of all these metals and metal alloys are very high. That's why we are even still searching for some inbound material which we can produce in a very low cost way. So the
At present, is there
manufacturing
any
process of
manufacturing,
steel, we get iron ore, we have to make it into steel, and then we have to mix it with other materials, and then we have to make the alloy, and that alloy, the complete manufacturing process is a very complicated process still. So we can come up with some simple manufacturing techniques, even we can reduce the cost of such systems.
at present, is any company is there, madam, in India?
There are a lot of steel manufacturing companies here, but those processes manufacturing vendors will get those things, they modify according to the need, and then they produce and they will give it back to you. So we have our own companies also, but still it's the complexity of the process makes it costly.
Okay.
Okay.
Okay, madam.
Thank
Thank
you.
you, madam. Thank
Yeah.
you, madam. Thank you.
Any other questions? So I hope I could answer all your doubt. Yeah,
Thank you
please.
very much for sharing your firm knowledge with us.
Thank
Will
you.
I wind up the morning session and lunch break,
Cannot
and
hear you.
we'll reassemble at 2 o'clock for the afternoon session.
Good afternoon to all. Am I audible?
Good afternoon, ma'am. You're audible, ma'am. We'll
Yeah,
start
I will
in
share the
another
screen.
5 minutes. No,
Another 5 minutes, is it? Okay.
yeah,
You
ma'am.
please let me know.
Okay, ma'am. Mm-hmm. A very good afternoon to all. Let us start afternoon session on ultra low power circuit design technique for low power IoT and biomedical system. And the speaker is Mr. Atmesh Srivastav.
Jasmita,
Yes, ma'am.
ma'am, you tell Suma madam to what?
Yes, ma'am. Okay, Suma ma'am is going to introduce the speaker. Suma ma'am, am I audible to you? Suma ma'am.
Chandrasekhar sir?
Yes, madam. I'm waiting for Suma madam to
Yeah.
start.
I think
She's there.
if she's facing any network issue means you can introduce yourself and
Yeah,
you
yeah.
can start.
Hello,
madam.
Jalaja madam.
Madam
Yes,
is
ma'am.
there.
Yes, ma'am. You can introduce the
Can we
Chandrasekhar
start?
Patil.
Yes,
Can
yes,
we
ma'am.
start?
Like you can introduce the speaker and you can start, ma'am.
Yeah.
Okay, thank you, ma'am.
I will share the screen.
Yes, ma'am.
Okay. Good afternoon to all. Today we'll be talking about the physical design with respect to 3D ICs and some of the commands to you need to work on this. That is nothing but we need to know the operating system other than the Windows. So Unix operating system is similar to our Linux. As we know, any operating system is a control program for a computer, or in our case, a network of computers where we can allocate computer resources and schedule tasks, etc., etc. I don't want to waste much time because he'll be going into the detail of the physical design. And this is another speaker of mine who is a student who is working on 3D ICs for biomedical applications in Cisco as a senior design engineer. So I think he will take you all by pinging right from his company. So I thought I'll just tell about the Unix operating system, which is a multi-user operating system where you can have control over every process that is done by Unix. And it also offers more control over the systems because we can schedule almost any process using the Unix operating system. There are many commands for using shortcuts and all. So I will leave it all to Chandrasekhar because I'm in Belagavi to see the release of our book. I'm with another student. So I requested Chandrasekhar to continue with this afternoon session. So he will be taking you all to the insight of the like what are the different commands which we need to know while we are doing any project in any company or even at the academics. I'll just display a few of those like ls minus a, which will tell about if you just give ls, it will just list the name of files. Similarly, ls minus l, what will happen, all that he'll be showing in detail. uh, and if you want to delete any files or rename any files, there are specific commands. And if you want to change directory and if you want to create new directory, copy files to another files, many such commands are there, which are also shortcuts. And these Unix systems are excellent in multitasking operations where they are, and also they score highly in providing high performance and reliability. And it is also portable and easy to install, user friendly, that allows user to have an easy time during the operation. Many such things are there which has key advantages. uh, because of the shortage of time, I'll just leave it to Chandrasekhar. He's doing his PhD under my guidance, almost in the verge of submission of his thesis. He's working on 3D ICs for a biomedical application, which cannot be revealed since still he has to submit his thesis. So I will leave it to Chandrasekhar. Thank you, Jalaja madam. Over to Chandrasekhar. Chandrasekhar, can you please take it over?
Thanks a lot, madam. Yeah, sure, madam. Thanks for
Okay.
your introduction and thanks a lot for giving
Yeah.
me this opportunity. Yeah,
Okay.
I'll take this, madam. Yeah, I'll share the screen and start.
Yeah.
Okay, good afternoon, everybody. My name is Chandrasekhar Patil, as already she introduced me. So I'll just go through, direct, I think, the practical applications, how the Unix looks like, and how we are working in industry. And okay, and I will also after that go through the, as she said, about the 3D IC, introduction in the industry. So usually what happens is, in our laptop we will be having a Linux, directly, but before that we need to have a one VPN. So through this we connect to the our Bengaluru DSL. Okay. After that, we need to enter into the our this one, that's called VNC. So I already entered in using this icon, the VNC viewer. So VNC viewer. If I double just click this, I just click the double time, so it will open this like this, a Phoenix environment for me. So this is other than completely window. Now I am inside my company's database, and wherein exactly means, I have entered into the my San Jose machines, actually San Jose servers, so Unix servers. So if I give, this is the my San Jose Unix server name, ASIC VM virtual machine SJC 174, that my command number is 111 now. Okay. So the first command we will go through is, as madam said, ls command. Ls means it will list out the number of files, directories, whichever are available in this path. This is the Unix path, means where we are in this different hierarchy. So means one slash is one directory, after that one other directory. So inside like that. So this is my working directory, where I have the digital and analog blocks to be designed inside the chip. So this is where I am. Okay. See, okay, this ls command now listed out these colorful, words here. So for example, if it is like lsf, this is a directory, which is a blue color, and this is a make file. This is just a text file, and these are also different text files. So we just to identify, I have been colored into the one of the file called dot CSHRC. Okay, this will be in the our mother directory, where where one has to have a as Unix logins like user ID and password immediately when the home directory will be created. So in that .csrc file is the one where we can add in the our commands, as well as we can make the aliases also. For example, to clear the screen, we have to use Unix command called clear. So I have made it as a alias as a C or CLS. It can I just for example, if I just press C here and enter button, so it does the same thing. Okay, so after that we have another command, ls minus a. So what it does is all. A means here all, even the hidden files will be there with the dot with the dot extension. So these are the hidden files. So these will also be listed actually with the this ls minus a. Ls minus lrt, she is listed another third very important command, where there's basic and very immediately to start with the Unix. Okay, that's what we have to come up with these first ls commands. Okay, what it does is lrt means now these are sorted as per the date of creation. The older will be listed at the top, the newer will be listed at the bottom. For example, see, my file very oldest is in 2021 July in this directory. Okay, after that 21. So wherever 22 is not there, it is just shown after that May 30. Okay, these are all newest one. So in this year, so it will come up to now. I have another directory created September 7th, where it has got some modifications inside. Because of that, it gets listed at the end, means the newer one, newest one. These are very useful, because if you have thousands of files here, you want to find out where exactly your file is listing now, where you may be edited or something. So this command is really helpful, ls minus lrt. Okay, after that I have another set of commands where I will go through this most top 50 useful Unix commands for VLSI engineers. Okay, so I think we have gone through all this. You are seeing my screen, right? Exactly. So clear also I have gone through. man is command to show the help. For example, man command means what manual page do you want to see. For example, man ls. So it gives what exactly ls command does, listing the directory content. So man is just like a help. Okay, so what are the its switches we can use it? Means ls minus a, ls minus capital A, almost all. Okay, like this. So there are so many switches you can use for the same command. So we use ls minus lrt. So this is one of them. Sort by modification time and newest first. So like this. So these are all different where we can get the man help, where it gives the if you don't know the command, or if you try to find out what exactly I can give. So this is very useful in the Unix libraries where we have made it. So PWD is the present working directory. Full form is, so or print working directory also they say. So it will say where exactly I am working on, means where exactly which directory I am. Okay, so CD now. Okay, I'll go to the. I said that there is a one directory here. So directory means we can go change directory with the CD command. CD LSF. If I go inside this LSF directory, there are so many here there are so many files. Right, again ls command will list out what are the files available here. Okay, cd back, if I use cd double dot and slash, what it will do is it will go back to the previous directory. Again I am in Innovus work directory. So if I go to lsf, here if I do present work pwd, so it is I am inside the work after this Innovus work and lsf. Okay, these are the you can use this double dots to go back to previous 2 directories, previous 3 directories, like this. So I went up to now previous 3 directories. So here I am. So 1, 2, third means I should be here. So it is what it is showing now, the pwd. Okay, so another command is make directory. I'll come back to my the previous, means cd and this hyphen, just hyphen gives go back to the previous, means wherever we were there before. So it will directly take back to the previous. Switching between that and the next previous directory, only cd dash will do. So if I do that, again I am back to the lsf directory inside C, even though I was in the third you know topmost directory, means the hierarchy was previous 3 directories n minus 3. Okay, now I will come back to my work directory here. So I'll try to create another directory. That is command is make directory, mkdir. For example, I have to give the make directory name. If I give just tpp, okay, this directory is created. To list out that, we don't know where exactly this will be always listing out as per the alphabetical manner, unless it is a capital first. Okay, B, C, D, like that. So if I do to go back to C inside my directory LRT, so my directory is now triple P is created here. Okay, so inside the triple P, again I have to, if I want to create some more directories, I can use make directory minus P as a switch. So inside the small p I have used triple P, and I want to have another A, B, C. I want to have another directory X, Y, Z. So it will be created. So now inside the triple P, the command is called tree and P. If I do that, you can see this 3 directories created. Tree is another very good command to see what are the other directories in the hierarchically they are available. XYZ, under that, under top of top on this, the top directory is ABC. For this, top directory is triple P. Okay, and like this we can see this is using the tree command also. Okay, there is one command called touch now. Touch, for example, if I give AA is just a name I'm using. So what it will do is I will do ls minus lrt. So it created a file called AA with the 0 bytes. So on this September 13th, 1:49 p.m. So this is actually San Jose time. Okay, usually I'll come back. We have date and other commands to see. So if I want to open this file, what is there in this file? 0 bytes. So gvim is the command to give the AA. So there is nothing actually. So this file is black. So you can see here only one first cursor goes here as a black. So this file is completely blank. So we can write something else here. Okay, for example, something I'll type. Next line. Next line. So it will have some bytes now. Where we can save this file. How do we use that? Go to the just shift this colon button. So it will take to the bottom of the file where we have to write W means write and quit. Okay, forcibly means we can give exclamation also. Okay, it enter now. So if we want to see this 0 bytes now, we'll have some bytes. Okay, 75 bytes has been written. So this file is now no more a blank file. It has 75. So you want to see quickly because this file is very small, we can use the command called cat AA. If I do whatever I've written there, you can see in directly standard output. Okay, this is seeing out soon after we give the command. This is called the standard output of the Unix. So or Linux, we can say. So this is the where content of the A is. Means these are the 4 lines that what I have typed in. Okay. So this is about touch file, and touch file I'm opening the file and writing into the file and coming back. So I will go to the copy commands now. Okay. Now this is AA file is created. Now I want to copy AA to some other file name called BB. So if I do that, CP is a command, CP AA BB. Again, if I do LRT, so BB is created with the same byte with a different timestamp here, 150 to 151. Okay, this content of this, you can see if you want to see the difference between the content of it, diff of AA and BB, if you give, see diff is 0. For example, now to test the difference, I will open the BB now. G is my alias to open in gvim. This is called gvim. Even VI editor also we can use it. There are 3-4 editors in the Unix: VI, gvim, Emacs, and one more is there. Emacs and another even text file opener. Okay, there are so many that we can just we can have our library, then we can use it. However, and means we are very well versed with the commands, those editors actually. So for example, now I will add another line here, something ada, and then I'll write this file and quit it. So if I do the same diff command, so if I use the arrow buttons in my keyboard, it will take to the previous commands also. Okay, what I am doing now is I am just pushing the commands like this. Okay, diff AA. So diff AA came. So you can repeat that command. It says now, okay, what are the differences? So this file, I removed some of the space there. So because of that, this has a space, but remaining text is same in the in this AA. And in BB, I added ADADA. So, and this is the same line. So like this, it will show what is the difference between the two files. Okay. Now I will take to next command called move. For example, if you want to rename the all these files, for example, use the command called move command. BB2 I will use CC. So move BB to CC. If I do, let's see completely it's moved, completely renamed. BB is no more anymore. Okay, no more in this list. Now BB completely become CC. So like this, move command is completely renaming of the whole file. Okay, remove is another command. To go to the next one, rm is the command remove. Remove minus rf means recursively as well as forcibly. So if I want to remove cc, now rm minus rf I can give. Otherwise, if I don't give rf, it will ask for the file like, do you really want to remove? See, for example, here, see, remove the regular file cc. If I give yes, y or n is the no. So it will remove it. Okay. Now if I do LRT again, there is no more, that file is like this. Okay, cat file I have already talked about, text one, and cat. Okay, I'll create another file. Copy this AA to BB. I will have two files. So for example, I want to put these two contents of the AA file, BB file into the CC. We can do that. Cat AA and BB, and you can push them to another file CC. Oh, sorry. No such file directory. Wait. Cat first AA to CC. So now CC is created. So all the content of AA, it is transferred to CC. Okay. So like this, we can transfer the even content of this to this also. So now if I open the CC, it is same as the what AA was there. Okay. Okay. So another one is there. For example, I have a license Innovus. Innovus is the tool. I have Innovus as my shell. Which, for example, I want to see which ICC shell. This is another command just to come about the what is the meaning of which. So ICC is another tool where I can use which ICC. If I give the binary executable for that tool or for that a complete path, it will show. Means it is installed inside the auto EDA tools bin directory where ICC shell executable file is there. So I can see, means by giving the which VI, which IC shell, we can find out their whereabout. Okay, VI is alias to Vim. So which VI, you can show it like this. Which Python, for example, Python is installed or not to run the command of the Python. I can see which Python. Okay, this is there in user bin Python. If it is not there installed here, so I cannot run my Python files. Okay, or it will show Python not found. So we have already installed here. There's so many. So it will have to show like this. Even tickle command, which tickle? Oh, tickle is not there. So like this. Which TCK. Okay. Coming to another command called history. See, whatever we typed in the previous, this command lines, this is called Unix prompt actually. So if you want to see, we can give the command HISTORY, history of whatever we type. See, we tried which tickle, which TCK, Python, ICC shell. So these are all listed from here. So it will list with some particular number we enter into, means from the this one. Okay, from the command number one. So but actually this will be very exhaustive if I go on doing this for months together. So first one will be deleted only up to I have made in my .csrc to 169 or up to I think 250 I have made. So in this Unix prompt I am at 169. So it is showing up to there from to here. So like this it will show. This is history command. So there are not much about history we can get it here. So we'll go to another command, chmod. Okay, change of the file, we'll see that. So if you give ls minus l, or I have made alias ll. If you give, it will say, see, I have just pressed ll double l. So I have made in this .csrc file where ls minus ll is equal to my ll. See here. So it will show alias ll means it is ls minus al. If you give ls minus al, so these are complete description of the every file and directory will be listed. For example, the first one is about the permissions of the file or directory. Second one is number of files inside that directory or a file. Means, for example, if quantity is 1, this is a text file here. Okay, this is a directory, so it has some 3 directories inside, so it will show as 3. So who is the owner of this? So my alias in this Unix environment is Chandrasekhar Patil. So they take first, every company, first 5 letters, and after that the second 2 letters. So 5. So Chand RPA is what they created as my Unix ID. Even my all the emails, everything, where my CEC password, everything is with this only. So okay, this is the owner of the file. You can see. So like this, who created what in this directory? Somebody may also come and create if I give the permission. Here I will talk about this permission now. So let's come to the third column. So this is my group directory, means I am in the common ASIC group where my project name is Krypton. So this is the group we are created for this, while working in this environment of this Unix prompt. Okay, this is the what I said about the the bytes, and this is the date of creation, and this is the time 2225, and this is the file name. Okay, this complete description will come when we give ls minus uh, l al or la. So here coming back to the this one, okay, permissions. So actually these will be divided into 3 3 3. Okay, first 3 will be for example, D means directory here. Okay, if it is just a one hyphen, it is a file. For example, pdnv.log is a file. After that, the 3 letters rwx, this is for the self, means I have this many permissions to make it on myself. And the second 3 will be okay, the full form of rwx means read, write, and execute. Okay, read, write, execute can be done. Second one is read, write, and yes, okay, I don't know what they added. Yes is okay. Read, write. Yes is the another. Usually we always cover only is it executable or not, or completely remove the. If you give hyphen hyphen, it will be completely removed of the permission. Okay, nobody can do this in this group. They can only read this. For example, here this file, if you see, I cannot even execute myself because I have removed this X permission here. That's why this file is white color. Okay, if it is executable, it will turn into like I have changed. Even anybody can change your colors as per your convenience. So here I have given the executable. This file can be executed. So that's why X will come. Okay, second 3 will be for the whole team, means my group, and next 3 will be for the others. So others can also see this if they are not coming under this CAG. So even they have the Unix in other business groups, so they can come and see my file. If I remove this permission, they can only read it. That means they can see the file. They cannot write or modify this file. Write means modify, and execute this file. So this kind of security is there in the Unix. So if I want to completely lock, in my directory, what I have to do is I go to this home directory, for example, till here I will show. In this project, we are there, Krypton project, we are the users. Up to here I will go. For example, I will just list out the LRT. These are the so many people, okay, working on different blocks of the project, the chip design. So these are all people. If I want to completely, where I am, this is ls minus Chandra. Okay, there is one more guy, Chart Tang is Charles directory, and this is my directory. If I do this, so these are all my subdirectories of the immediate Chandar PA. Into that I went to the in the one of these. Okay, now what I was talking about is if I want to change this complete chmod command. Okay, the chmod is change the mode. The command 777 is the complete permission, means anybody can go into this directory and change or modify my my all the files. So this is called 777, like that 755 754. Okay, this all different read, write, X for the owner. So like this we can go on changing this. One I will change and show you. I will go back to my previous directory. where I was in work directory. So in this, I created a file called ABBCC chmod minus R. If it is a directory, we should give R. If it is a file also, we can give R. But it's a common habit, we made it minus R. Then if I give 777cc, the last file, okay, now its permissions are being changed. So it becomes read write executable. This is a file, that's why it's a dash. It's not a directory. So read write executable for the whole team, read write executable for others also. Anybody can come or delete this file also. If I give just one permission, for example, if I can change this to 755, we know, I think Wi-Fi is there. This again, 5 is a binary. In the hex format, we read directly here 755. Up to 7 we can use 1 to 7. So this 3 in the 3 digits, it will be written like this. So let's see how it is changed. 755 when I give. Okay, see, now it is changed to read permission or execute permission for myself. My team can do read, cannot write, but execute. Even others can read, cannot write, and execute. So they can just execute and read it. They cannot even touch, delete or modify this file. So I can only do this. So 755 is another best command we use. Okay, touch file. Touch is another file. I think I have already talked about this. Means it will just create a blank file. File 1, file 2, file 3 at a time we can create. That's one of it. It's not a head. Okay, head is a command. Head and tail are the command. For example, I have this one is a very big file. Let me just open this head. If I give just a file name TypeScript, so it will use some default about some 10 to 15 lines of the opening of this file, means the top head of this file. If I open and show you the same file, G TypeScript, so it is shown up to all rights reserved worldwide. So to search immediately, this is the slash command you can use. You can just paste it. All rights up to here, it is completely open from the first line to last line. If you want to set the numbers, for example, how many lines it has it has listed, you can see up to top 10, right? Some 10 lines it is listed with the head command. So 1 is the line number 1. So but it will not be written, but it is just indicative. Okay, if I go to shift G, this end of the file. So end of the file, the line number is 57,933. So like this, we have to code for doing the works in Unix, right? So Unix scripting. So at that time, we use this, setting the line and going to the line. For example, if one is referring, we can just say, like, go to line number this, and then, okay, change this command or something like this. That's why this how it is very useful in setting the line numbers also in the GVim or Vim VI editors. Okay, tail is another command. Again, it will show the top last 10 lines of the same file. If I use head file and file name, tail is a command, and after that is file name. So this last 10 lines will be like this in this file. Can show you that. Should be yes. Okay. See, echo 0 m there here. Okay, twk is there here. So don't worry about this. This comes like this while visualizing. So I need to set up to remove this also. Okay, this no, tilde yep. So this this symbol. Okay, this is happening for my JVM, but you just ignore it, because what happens is when we enter, the enter command is always shown like this for me. Okay, see, for example, here in Innova's 47th line, what I did, GUI show, and after that I entered with the enter button, so it is shown like this. Okay, let's not worry about that. Come to the sort. Sorting of the files can also be done. Sort takes, I think, a little bit time. I think I will, okay, it will take time. I will kill this because I have to go to, we'll come back to this later. Unique is also again same, it takes a time while after giving. More and less we will go now. Okay, more and less are the two commands. We can just visualize the file, but with the help of more and less. What it does is LRT. More means it will just give the file in detail. For example, I was opening this big file which is having 6,000 6000k of the bytes. So sorry, this I should give. You have to give the TypeScript more. Okay, so it immediately in the from the line number 1 it opens in the this one itself in the standard output. So if I give just pressing enter, goes on opening the bottom the next portion of the file. Okay, and less is another one. Usually we use more, uses the more memory to read the file at a time, or less only. This is the difference. TypeScript is the file name. Less, it will open in the lesser memory, but yeah, we can still go to the whichever line number you want or whichever portion you want. So usually the big files, not to consume more memory at a time, GVM uses all the memory and then only it displays in the new window. So these are the less and more are very quicker in Unix, so that we can open those very big files. In mega gigabytes also the files will be there in the physical design. So grep is the command where it will grep something in the file. For example, I'll use command grep innovus. Innovus is the one word, the tool name in the TypeScript. We have seen that innovus word was there inside. If I do see wherever the innovus a word was there, so it has grep complete line. So like this in 31, 32, so suddenly 30 and 40. So wherever innovus was there, it is all grepped. For example, if you want to count how many of them were there, you have to pipe it. This is a pipe command where it is a OR. You can use in electronics OR, right? So WC minus L, it will give how many of them are appearing. So there are 404 number of innovus is there in the file TypeScript. So this you can pipe is another Unix next level command, not only basic like grep. So we can nest all the commands like this, go on nesting. Even we can use out command to nesting with this. So it will give more usage of the Unix. Actually, that's a little bit advanced. Okay, we'll go through that also maybe now. If command I have talked about top bottom. Okay, I'll go to US command. PS. PS is it is nothing but process status. Okay, process for the current shell. PS means the what are the processes running in this. Okay, PS minus U is my PS minus U, the user one. Only it will list all the process means whatever commands. One process is maybe one command. I have given one command sleep up to this much, so this is also running. So whatever the process were there which are running behind at present also, I have also running PTECO at some other directory. So this is also as one of the process. This is process owner, process ID. When we want to kill the process, for example, we have to use kill command. Kill minus P is the process ID. If I kill this, it will be completely killed. So I don't want to kill because my prime time is running at the with this process ID. So I'll just leave it. Wait, maybe I can kill this sleep command where it is sleeping. Okay, maybe P I shouldn't use. Okay, this process is killed now. Otherwise, if I use some other ambiguity like this one, so it will just unknown signal or kill minus L for the listing of them. So it will suggest something, okay, to do this if you do mistakes like this. So P kill was the command actually. Yeah, P kill, and if I do this same, so it will do the process kill also. But it's still already killed. It didn't say that it's already killed or not existing. So like this, we can use the kill command and the process also. one more command. If we have entered in some other Unix, we don't know who we are. So we can give who am I. So it will say, okay, he is the owner of this Unix in the name of Chandar PA. Who am I is the command. Okay, users use free. Okay, these are all not that much useful to see. Okay, I'll just go to the date and time. A date, if we give, it will show the date of the today's date, and it will what standard timing is there. Means, for example, I am in San Jose, America, the California time. So this says that on Tuesday, September 3rd, 2 a.m. Okay, for them 2:15 a.m. and 9 second in PDT Pacific. Pacific time is a PDT in 2022. So this is the date command says. If we give time command, it's very clumsy. We have to understand this. That's why to know what time is in, for example, we are working on or something. So we just need to give date. Okay. If I entered into my India servers, so it will show my IST here instead of PDT, and it will show my India time now. Maybe the same, the date is 13 September and 2:45 p.m. like that. This is 2:15. That is AM for them. So it is 24 hours format. So it will convert into like train time. Means 24 hours, 24 or something like that. 23, 24:00 or 23 some timings, whatever. This one is there. Okay, these are the top 50 almost. Bash version, host name, you can try here. Host name means which host name. It is saying that I'm in the host ASIC VM SJC 174. So like this, okay. This are top 50. I think I have finished off. I have left with any more comments. These are the just basic, and we use this very extensively. And I will also show some gun zip and zipping of the file and the tarring of the file also. For example, if I do gzip, maybe gzip works. Let me say cc gzip. Oh, sorry, spell mistake. Yes, it is now zipped. See, .gz is extension, so the file is now cc.gz. Okay, if we want to unzip them, can use gunzip is the command. Maybe this back to this. So it is now gunzip means back to the original file with the 75 bytes. Okay, cc back, that file extension is gone and it has come back to here. Okay, like this, there are many commands that we can work on the file separately, directories, and removing of the file, moving of the file, change the name of the files, and opening of the file, head and tail with immediate and more or less. So like this we can do. PS is the that process IDs that we can see. Mail is the command. For example, I want to mail one of the file here. For example, I can show that also. Mail X is the command, Unix command. I will give attachment. My file is cc, give attachment. I want to mail to my own Cisco ID. So Chandar PA, if I give, okay, it will ask what is the subject name. I say cc file, my subject name. Then I have to give just dot. So it is now mailed it. If I come back here in my Outlook Express, so it has come here. I can show you that file. Okay. In time. Okay, this file has come here. Can you see? If you want to open this file, okay, just open it. That text. So whatever I typed in, so now it came to my Unix, environment. Sorry, my Windows one. Okay, sorry. From Unix to now I'm in Windows, where my Outlook Express is there, right, for my email communications. Like this, we we have any, that like, my tool related, yeah, this one, we have, set of commands where we will just make them to send it here, so that even though I'm outside or somewhere, I can just view this file, or I can just send this file to for any other technical discussion with somebody, right? For example, here I have a one tool where it did a insert DFT, and these are the results. Okay, so it says insert DFT run is clean, and it has finished at this time, number 13 PDT, and my insert DFT results, it has attached to here. So what are the, how many errors, what are my, results, outcomes. So we have grabbed them and put it in a file, and that file is attached to this email, and it has come here. So whenever we are running, that our Unix processes there, so we have, set of, these commands where it will go on giving the information about the run, what is going on. We don't have to again go and see there also. We can just visualize this, and we can discuss on this technically also. Okay, this is my PT results where reg out violations are these many, and my regin violations are these many. Okay, for the hold violation, these are the setup max. So, and total number of, violation. We can write anything, whatever we want. Even we can attach the pictures also. For example, in the LBS file, we get always some pictures attached, where this is done by, my runtime is this much, it will add, maybe have some pictures they have added here. We can open them and see also. Okay. Okay, this takes a little time because I have removed all those GIF because it takes a time, and it loading time also. Yes, we just see this text, subject name. Okay, LBS has been successfully. So like this. There are these are the most of the advantages, or Unix environment while working. One can have will be well versed with this kind of. These are all basic commands actually. Not much I'm going through. There are some other also where it will do out also, out command. For example, I will show one out command. PT directory I will go. Setup summary. Okay, I'll just open this file. For example, this file has very less content where all the violations are fixed. Hold summary. Okay, this has more content. Let's open in the parallel also. G hold some RPT. Okay, this is the file. So it is listed out. Regin violations are this many, 4 paths, and like this. Okay. For example, using the out command, how I want to go with this column wise one. This is the first column, second column, third column. For example, what I will do, the file name is now cat wholesome.prt. I will pipe this file, okay, with another set of commands of the Unix. There's awk command where this is the format to print $1 and close it. If you just enter, it will give my first column here. So it will just print out this first one. It is all omitted second one. If I want 0, 1, 2, 3, fourth one, so I have to just make this 4 here. Okay. The fourth one is printed out where it is 1, 2, 3, 4. 4, 4, 4 are there in this path. Okay, this path is listed. The whatever there in the whole column, it will be listed. Okay, like this, we what we do is we go on, in this fourth one, I just want to grab again paths, whether in the big file what happens. These are the basic commands. We go on nesting and find out what really want to search or something instead of going line by line. So for example, if it is a huge 1 gigabyte of file, so I don't have to find out. I'll just use this, whether my searching word is found or not. Means, for example, whether it's failed or passed in some of the procs we use, uh, uh, procedures, right, while we're writing in the tickle command, because the tools runs in the tickle. So we have to be well versed with the tickle scripting also, in that whether in that script or in that output of the .log file is the .log is the output of that file. So whether it's passed or not, like this, we go on nesting those commands and get whatever we want. Okay, I think, yeah, this is a little bit, this is more on the Linux commands. Shall I switch back to physical design activity, how the industry it is done? Okay. So okay, this is whatever you're seeing. This is one of the tool. It is called Innovus. Okay, Innovus. This is the layout of the one of the block in the physical one of the block inside the chip. Okay, there are so many blocks will be like this. So they will be tiled one after the other, and after that top level chip is designed. And this is the same way. Whatever you are seeing here, these are the some uh, small square boxes. These are the memories. This, if I click on them, this is the connectivity it is showing. Where it is talking to another standard cells, or this one is what another memory. So it will just show the connectivity. Okay. Now let's come back this physical design activity. So when you look at this layout, this is these are the pins actually. Okay, this pin is I can just show. There are two pins. If you zoom in, so triangular shape going inside means this is the input pin. If it is this side left to right, the pointing to, then it is output. So it is shown in here. If I give Q, so it clearly says fixed. It is in metal 4. Okay, what is the pin name? This is direction is in. Okay, like this. Or in-out pins and input pins like this. There are so many pins will be there where it will enter the signal with this. It will take the signal and talk inside, right? So the signal will be gone inside here, and it is talking to this buffer first. And this buffer, when I click on this, it goes to the another cell where it is talking to another logic gate or memory directly. So like this, okay. This is the connectivity it shows you. These are called the fly lines, which are shown in the blue color. So these are the memories. Memories are register files, SRAMs or TCAMs also. Okay. These are the big memories actually. If I give Q as a button, so it will just give what is the memory name, what is its D box means, what is its size, and what is the name of it. Okay. So I'll show in the physical design activity what happens in step by step. So first we design, we define the first what is the the block areas required. So rectangular, rectilinear, okay, like this. For example, in this case, I will show another block I have already opened for you to show. So this has not rectangular. See here, it has steps like structure here left like this, because another block in the top level will sit on top of it like this. So that will become completely square. So because of that, in this block we have to design like this only. Okay. Soon after we make this boundary line, we have to have the one blockages here. Boundary to the first cell which is available. If I make it on blockage here, so the complete red color, there's a brown color blockage has come here. So in this there is no cell is sitting. Okay, this is completely hard block. If I remove this switch off, so this is the first cell, from the left to this one, it is sitting. These are the boundary cells actually. This is one set, this vertical one. This is the one physical cells. This is end cap. We say these are the end cap cells. Means your row is getting ended here. Okay, for every, these are the standard cells inside. This is completely fully filled with logical cells, that and nor and whatever that gates are there. Those along with that filler cells. These are the actually fillers. And after the end caps, we have to fill this the blank area with the fillers. We know all the reasons why, because it's required in physical design, right? Yeah, this is one. This is called ESD cell. Okay, used for the ESD protection. This is a TCD cell. It is a phantom cell. Where my foundry, for example, this is targeted to TSMC. They have just said that use this cell very next to every 2 microns, 2000 microns, 2 mm area. So I have to add this cell T. But after we adding this cell, even though we don't know what is the meaning of this cell, this is a phantom cell we call, because it's nowhere it will be connected. they will replace this cell at the time of manufacturing. They will add their own cell here, so that it will helpful for them. So that is also confidential while you are designing. They just say use these are the rules and use these cells in between in your design for every 2000 micron, that is 2 mm area. So next cell will be for this to use will be another 2 mm somewhere here. Okay, microns later. 1000, 2000 somewhere here. R is missed. I'll just remove the standard cell. It's taking time. Because sometimes what happens if the pin is coming here, we cannot add it. So maybe we can use it in the next one. For example, here the same set of cells, the ESD and TCD, where and all they have used. I will show you. Okay, see, this is one it is used. I'll clear off this. Okay, after this they are not used because the pins are coming. So I have used it. The next one is here, another set. Okay, internet is too slow because I have done the tunneling because to enter into that. So other set is here. Okay, this is the scale. Okay, coming to here, the on-chip components. This is completely having one set of IPs here. Actually, this is the SerDes IP. We have added these SerDes IPs where with the very sitting next to each other. We have set up rules how to add in. Only 4 should be there, 5 should be there, something like that, given by the IP vendor, and we added those along with our digital logic here. This is completely self-contained cell. So digital logic will be sitting like this. Okay, I'll remove the physical cells. So I will have only the standard cells. So for example, physical cell will be just connecting. So if I click them, this will show the connectivity. So I'll talk about the row also. I forgot to, because to make it very clear. So there will be rows. So it will sit, one standard cell will sit in between the one row. So this is one row height. In that, these are the smaller vertical lines are just showing that how much of the one smaller unit, that is unit grid. So after that, how much multiple of this cell is 1, 2, 3, 4, 5, 6 multiples of the one unit tile. This standard cell is. This standard cell, what this standard cell is, just to know that, just query it. It will show this is SVT cell with a delay cell. Okay, with this complete name, which is having drive strength of 1. The end number name will show as drive strength of 1. Okay, the physical name of this inside this design is SerDes spool macro, and this is the data 33. So like this, the hierarchy of the names also will be applied because it is coming from the RTL actually. So this delay cell, the name is this, and its a physical B box is this one, X and Y values, coordinates. This location is this one, X and value, and this complete B box area will be XY, XY, lower left here and top right here. So this value will be one, and name of this, and whether the place statement is the placed or routed like this. There are different attributes for it. So those will be there applied on this. Okay, this is about physical design activity one has to do at the time of designing. This is analog block. So this is connected like this and routed up to here. You can see this square shape. If I click here. Okay, to see the metals, how they are routed. This is, I will on metal 0. So metal 0 will be to the just a horizontal blue color line. You can see this blue color line. This is carrying the VDD current, the voltage. Okay, sorry. So here the VSS voltage will be supplied at the bottom. So like this, every line will have VDD VSS to supply the power to the standard cells. Okay, these are the pins, the another horizontal red color on the same metal 0. If I make it via 0, so after top of it, say via have come here, via the next one sitting here, this for this pin. So after that, metal 1 will sit on it. So the connectivity from the BOL layer, the standard cell now, from metal 0 to metal 1 it has come. Okay, like this we can go and check how it is got routed. So it is routed in metal 1 after the metal 0 completely like this. If I click this, how much long distance it has gone. See, the routing has happened like this. Okay, unless it is touching another cell somewhere here or something. Okay, so means another end point where it will go and end its connectivity. For example, here it came here, it taken another path, it is in different metal, that's why it is just showing a line. So it coming back and touching this pin, okay, pin of the another standard cell where we saw that as a fly line, right? That one. So I'll remove this for the clarity, the bottom layers. So I mean we are 2. So this cell, it is connected to this pin. And to see, even we can see here, the net name of this connectivity is this one, data 33. Okay, these are big names actually given by the the tool sometimes, and starting from the RTL, then taking from the base as the, okay, like this we can see completely. Even we can see power nets also here, how the power is stitched from the metal AP layer. AP is the highest layer where one has to use in the physical design. See, this much big is the the horizontal one metal is one piece of metal in the AP layer. After that, if I do, because we know in physical design all the metals will be like Manhattan routing. One will be horizontal, one will be vertical. So in between that, the connectivity happens. That's called via. So through that via, these connections will be made. Okay, this is the via for AP, and this will connect to the vertical. This is the green color is the vertical. So this green color vertical, I think it is getting selected my rows. I'll just remove the rows. Deselect. So you can just select here. So this one is getting connected with this metal horizontal with this vias here, and this is the connectivity VSS. So this now green color will also be VSS. Can you see here? Selected will be the white letter VSS, and this is a VSS. Like this, without any short, all the VDD separately, VS separately, the power will be stitched till the metal 0. Okay, in the BOA layer. So this is done by the tool actually, that's called metal routing, P and R placement. After the placement of the standard cell is done, this metal routing is done, and power stitching is entirely different. We do it at the time of soon after the floor plan is done. Okay, uh, let's talk about those steps, how the chips are made in the industry or any physical design activity. So I think I'll go through the for that the PPT. Maybe now we have left with another 50 minutes. Okay, I just went through what are the metals here, and just to recap, and standard cells and the physical only cells where the pillar cells are there, and how the routing is happened, and what are the top layers. And this is completely sorry, for example, this block I am showing is one of the analog block where these IPs will be given from the different people, and we just to make our sorry different people, we just add our digital component in it and make this block working, because digital component also has to be required to communicate to the outside next block. So because we have to, why the digital components are required, because this will just give the signal input and output. For that, to reach the output or going out here to communicate, we should have equal distance and all those parameters, equal skew. So to maintain that, we have different rules, set of rules we have to keep them here. Okay, if I do metal 1 on, I can show you why I say it is completely IP block, because it will have the till the bumps also. See, these are the top bumps on the top of the complete block. So until this we cannot route anything inside, we can just use its pinouts. Okay, till AP layer, this is that AP layer is this is a 7 nanometer technology, we have till 17 layers as the their total BOL layers. So in the lower technology, we had up to 10 also in before 40 nanometer and 50. So after that, these metals are getting stacked so many. This is a scheme of the metal. We say this is defined by the foundries. Usually in 7 nanometer, everybody uses up to metal 17 because more number of logic is there, and to reduce the congestion of the routing, to get the tracks for the routing, we have to increase the number of layers also. So in 3 nanometer, it will be another +2, up to 19 it will go. Okay, this is 7 and 2, hence we have up to AP layer 17 as a AP layer. So AP layer for the lower layer, for example, if it is only up to 10 layers, then it will be AP will be shown here, AP in bracket, it will be shown as M10. Like this. These are the complete, chip, bumps, round bumps. After this, it will be attached to the package. Okay. So this is how one block I am showing here. This is one, and another one, another block I have already opened up to show. That is a digital block where we don't have this AP, because after this, the block owner of the top level, what he has to do is he has to add those bumps here. He will stitch those bumps in AP layer. Okay, so here AP will be just blank. So after this, he will add, but he will remove these two layers to from metal 15 to 16, and after that, just for the power connectivity to check our IR issues, anything, we just made it a dummy layer. But at the time of tape out, that means manufacturing time, in the top layer, there will 15, 16, 17, and he will add the bump connection and make it available here, so that it will be completely manufacturable. Okay, this is about the digital block. There I have shown the memory is also inside, where another set of there are also IPs where the SRAMs will be there. So this is another big block actually. This is a module in module, say, that is hierarchy in hierarchy design. We have another block in the block. So inside this also there are so many memories. Here controllability is only up to the top level, means to control inside this block, which I have highlighted here, we have another layout to be opened. There we have to do changes to meet setup code or buffering, anything, routing. After that, we have to bring it here and then stitch together and then make this layout. So like this hierarchy in hierarchy, blockwise, and making use of complete IP inside the chip. So such components that one has to be taking care in the time of physical design activity. Okay, I think this is all about physical design activity in the one in the industry will take place. I'll also go through RTL to GDS direct structure. Okay, just quickly. For example, I am in this design. I'll take to again digital design only. Maybe yeah, whatever design. So how the RTL will be taken, and after that how the placement routing will be done. So I'll just show that I am in the version of T1 ECO20. I will go to DCT directory. I will go inputs Verilog in. Okay, LL, only one file. I'll open this file. G of, just enter files list. Okay, this is the complete RTL where the Verilog structures are written. Okay, with the different modules, and the top layer, top module, and after that sub modules. So like this is actual RTL. This RTL. If I do GF on sitting on one of the lines, so it takes to the link to the another file. This is also very good command to learn. So this opened this file directly. Auto define defines.v file. Okay, this is a module where the RTL owners, RTL complete is another complete job in in the physical design. They will write only this much code because it's so complex. One cannot do complete RTL to GDS2. We can take the RTL written by somebody, which is synthesizable RTL, and then we can use that Verilog file read by the tool, and the physical activity design starts from here when the RTL is ready and design is working with the so many sets of tests there. So with this, and after that, we use the tool called DCT. So I am in very low. So I will go to output of the DCT. Okay, these are the different files generated by the DCT tool. So we are only concerned with the final one file, which is one netlist. Okay, after that Verilog code is read in. So this is the netlist which goes into the physical design of the that 1 minute. Okay, sorry for that option. So this says that Synopsys tool DC Ultra has been used in the wire load model. Okay, this is the version of the tool, and this is the complete synthesized netlist. So it has used directly gates here now. You can see here FDPQ is a one of the D flop. The name of this, we just recognize this because we extensively use those. So it has a D input, clock as another input, Q as output. So this is connected with the .SO update clock and update out as the net connecting to it. If you draw this, in the physically, we can draw a complete circuit by using this text format. Okay, D flop is connected with D. These are the net names. The clock name is a capture clock, and after that, this will be in the another module. It will be get connected somewhere else till the port. Okay, port of that I have shown the ports, input and output ports, or input ports. So like that. So it will be completely connected net design, which is synthesized, but in the form of text. So one has to be very extensively changing of these nets and connectivity in the text format itself will be a very good useful skill in the physical design also. Okay, so these things, because this all in the text, big text, so that's why the Unix commands and will come as a handy, or the scripting will come as a handy to work on this kind of activity. Okay, this is the netlist I shown. After that, we go to PNR tool. PNR tool is called Innovus. The work directory I have there. In the outputs, I will just show, or maybe here it's the okay. So we did floor plan at the beginning of this design. Floor plan.in is the that file name it's saved in, which I opened in a layout, which I can show you here like this. Okay. So floor plan. After that, I did init design, means just a initialization of the timings and all the dot library, TLU plus libraries, dib files. So everything will be done in the init design. Placement of the design will be done in the place design. All the standard cell will be now, memories will be sitting inside. Init, they will be still outside. Floor plan is nothing but we just made a complete power planning. Power stitching is done here, and just made outer port placement without any DRCs, and the memory placement only. Okay, standard cell will be placed only at the time of place is done. After that, CTS means clock tree synthesis. That is, a clock has to be built from the clock port to reach all the sync points. Sync points means our memories as well as the flops, not the standard cells, because standard cell is a combinational logic. It doesn't require the clock. Only these will run with the clock, where the logic will get changed from their input to the output because of the clock. So clock is a vital force here. So post CTS, some optimization will be done, and actually there are very deep subject if we go through. I'll just tell the steps. After that, routing. Actual routing happens of the metal at this stage, route.in. Okay. And post route is another optimization. on the route stage it will take. And after that, in design opti, we say is another tool will be called, and virtual metal fill is done, and again some optimization on the timing will be done in this. And after that, the chip finish. Chip finish activity means adding all the now left out free space with the filler cell I had shown. So that will be done here. Double VR will be also inserted to make the DFM and DFY another big subject to talk about. So after that, this design now will be taken to the DRC and DLBSs. So I'll go to another tool called to ICV. Sorry. T1 only. Okay. ICV I will go. This another tool. Actually, if you look at from this point, so all the directories are with a tool wise, they are listed here. Can you see? So one in the physical design, these are all the tools used to make it the chip working. One is DCT, maybe ICC2 you can use in the Quantus. Okay, these tools are different for different checks actually on the inside the layout. Okay, so major I will go through the placement and routing is enormous, and FM we do okay. Caliber tool also we use for that, and verif means it's a DRC Elvis clean. I will check. After that, star is extraction of the metals, and where the real toe, that is a RLC value will be calculated, and after that this will be check that the actual timings in the prime time. PT is another tool. These are the different vendors given. For example, PT and DC is from the Synopsys, and mix and match also we can do with the different EDA vendors. These are all EDA tools actually. Innovus is from Cadence. Okay, ICV again from Synopsys, that is very directly created. Okay, we use another called RHSC, that is from Apache, Gen Apache, that is from different vendor. Okay, so like this, different tools will be used for testing of the chip. So now I will directly go to very work directory. In this separately files will be there. Okay, I'll remove this. Okay. So DRC directly inside this, I'll just show how many DRCs after that will be seen in the layout errors. Okay, this is the ESD violation has come, the 65 violation ESD. Okay, like this. These are the DRCs. One has to go and fix back by observing this in the text format. One can also directly load in the design, and it takes to where exactly the problem is that we need to clean the DRC. Clean DRC means the width and spacing of the metals and the standard cells. And there are so many rules actually about nanometer wise, they go on changing. So DRC should be clean. It should show as a clean instead of violations. I am in the T1 version, so my DRC are not clean. It's the first version. After that, T1.ECO, there are the different ECOs will go on the same design by copying the main design. So that's how we go on cleaning the timing as well as DRC and whatever other issues we have, RHSC, voltage drop, signal EM, all those things. Okay. This is the directory structure about this. Very, I will go to star now. Star outputs. Okay, this is the one netlist, and RC is the our resistance and capacitance. It will be put into the one file format called GPD. It is almost binary format. Just tool reads it. We just control through the commands in that tool. So I just shown how exactly the RC extraction is done. So coming back to PT. Sorry, CD2. Work directory. So okay, these are the set of corners we make in, so that we make OCV variations and check for whether for all the on-chip variations after the manufacturing, will it work? So set of hold, we make it. We make the wires as the C best, R worst, and something like that. C is the capacitance here, R is the resistance here. Okay, and different temperatures with the 0 degree centigrade and 125 degree centigrade. Okay, this corner will apply all the condition of making this 125 degree centigrade on the wires, means on the metals, and this is the hold corner. We make the cell to work as FF very fast, right, in the CMOS. So like this, set up separately, hold separately, we make it, and we summarize that in the tool, and after that we just check PT summary. And done. Okay. CK is alias PT sum K is a command where, okay, it is now listing for me all the details. Okay, so my setup corner in the reg to reg violation is 0 0. Okay, like this. Into reg having completely met with the 4NS. Actually, this is wrapped back here. This is second line. See here now. So, these are the violations are met or not. See, this is violated into reg violations, or violated here with the 2 violations with the 18 PS, and total TNS is 37. So we have made our own script to, for example, I just typed alias PT sum K. So means I am sourcing this file. I just typed PT sum K in my Unix. So if I open this file, what it is doing is, this is called scripting. Okay, this is just using grep command. Okay, A6 is the number of lines in the top where it will look for the this word core clock, and this is the directory work. Go inside this report directory and then take that grepping of these lines, and it will put in .junk file. After that, that will be processed. So like this, we have to use if and loops and everything as the syntax says, and then make it to appear as per this format what I'm looking for. So this is another work that one has to do in physical design. So I just listed out what are my IR drops happened in the going inside the IR directory. Okay, are all 0 violations, and here floor plan violations are only 65, DRCs are 105. Okay, antennas are 0, antenna violations. LVS is successfully passing. It will show otherwise failing. So like this scrapping and everything, these commands will help us when working with the this kind of Unix environment. This is a summary actually. Okay, so this is all about the physical design. I think what I will do is I will again come back to my presentation, because we are left with another half an hour. Okay, so in this, we'll go through how the 3D ICs are made. It is a new advancement in the technology. Whatever I shown, it was a 2-dimensional IC, where the big chip, about 2 inches by 2 inch chips are made for medical equipments and all. Okay, so which application that will not be revealed. So we'll just go through how exactly 3D ICs are made and how the advancements are there in the industry, in the physical design. Okay, coming back to the first slide introduction. As we see in the decades, okay, from the 1970, we draw the graph, we are seeing so much advancement in the electronics. What advancement is happening? We are going into nanometer technology from the micrometer technology. The 350 nanometer. Now we are at 7.5, 7, and 3 nanometer, even 1 Armstrong also. Right. So it is a gate length measurement usually. So if you look at this graph, the stars blue color will show how the years are passed. Is the billions, 2.3 billions of the transistor we are able to put into the same area that what previously we used before. Okay, the left side is a MOSFET gate length. So The red color will show, the drastic decrease in the MOSFET, gate length from almost 300 or 250 in nanometer to we are at 7.5. This is what the graph says. This has 3 actually. So another one is at the right side, transistor per processor, processor chip. Okay, that's what is 2.3 billion transistors now per processor chip. We are putting it 10 raised to 9. So like this, this graph gives completely what exactly the present industry is going at actually. Okay, gate length versus the transistor integration, along with our decades of years. Every 10 years actually is one decade. So from 1970 to 2020 now, 20 to 30 it will be. Can draw that later. Okay, present challenges in a single nanometer technology, that we'll talk about this after how the technology is evolved after seeing that. Okay, when I entered in about some 20 years back, it was about some in 1997 to 2000, it was just 350 nanometer and 250 nanometer where the chips, okay, where mobiles were not at there at that time. They just introduced after 180 nanometer and 130 nanometer. We are doing the electronics chips with the 250 nanometer and 350 nanometer. We know how the parameter, how the paradigm shift happened between these 352. We are at 5 nanometer. Now I am working at 7 and 5 nanometer, and we are approaching in few years that 1 nanometer or 10 angstrom. So as per the Moore's law, every 1.5 year, the integration goes as a double inside the same area of the chip. Okay, so this is how it's calculated. If you take the area as 1 by 1 unit, if you divide it half, that means exactly cut it 50% of this, 50% of this. This 1 by 4 portion will come in, right? So 0.5, 0.5. So if you take this relation, again if you cut it half, means the double integration will happen in 0.25 into 0.25 area. So it is nothing but square root of 2, that is 1.4. So that's how, if you, for example, 350 square root of 2 almost will come 250, like that. Okay, for example, 180 is there here. After that, who will decide this? It will not be just decided based on the feasibility or the DFM, design for manufacturability, possibility actually. It is depends on the calculation, that we do it here. That where square root of 180 divided by 1.4, the square root of 2, it will give after 180 what is the next target will be 130. So 130 will come. So it is near about number. Okay, because it will come in points, so it will be, they will be rounding off. That's how the technology nanometer nodes are decided, right? So coming to the
Sir,
yeah.
square root, why square root of 2 is considered?
Because of this, we are doubling in the area. For example, I have shown here, right? One into 1. You want to completely double it, 0.5 to 0.5.
Okay.
Yeah.
Thank you.
So like this, got it? Yeah. So because of this constant value will be square root of 2. So that's why the technology nodes will be, I think, decided. So it will not be exactly, but roundabout they will make it after that. Okay. So coming to the challenges, we have so much challenges to make this happen. It will not happen without working of so many people and so much of efforts. So one is the gate length scaling. Can make it up to, even though it is possible to make up to less than now 1 angstrom. Okay, that is, sorry, 1 nanometer. That is nothing but equals to 10 angstroms. 1 nanometer is equal to 10 angstrom. We can go on making this even though the feasibility is there, means using the OPC methods and all those optical proximity, optical proximity correction, OPC full form is. Okay, using that we can still manufacture, but chip will not work at all. So what to do? Because of the material property, chip will not work. So we have, some people have come up with the strained silicon, means we are introducing the stress inside it. So that is, sorry, that stress will create the mobility of the electrons or holes inside the CMOS. That's how the CMOS will start working. That's called strained silicon. Okay, so this is got introduced when we are going down towards the technology, because we have to make it work, because so much electronics need to be fitted in and so much logic is going to come. It is not like only if, because why logic will increase, because so much work has to be done. For example, one mobile everything has to be there. Bluetooth should be there, Bluetooth logic should be added. It should have IR also there. It should have communication protocols, though, so that related electronics should be there. Whether it is again some other applications to control your TV also, so that IR communication also, that IR one sensors and everything should be there. So like this, electronics goes on with a different flavors because of the requirement of the the product they make, whatever it may be. It may be, I'm just taking an example of mobile, so it is there in everywhere now. The new technology is coming for the cars. Okay, the cars is everybody everywhere. They started with small companies to make the dumb cars to smart cars. Like TV happened smart one, right? Because of that CRT time, it was nothing, only just channel we used to change. Now TV can access the internet, it became a smart. TV can talk to you, and like there's so many things, right, that we are seeing it today. So such things uh, are coming into even for the cars also. That is different technology. Okay, like this, the challenges will come when we go on getting these so many features to add inside the chip also. So metal pitches and width are getting scaled because we are going towards lower technology. The scaling of the metal width will also be half. It needs to be cut half, 1 nanometer to half nanometer, so that to routing can happen. But because of the skin effect, okay, surface scattering is another difficulty. Okay, these are limiting the technology, but still we have to break through these and find out some solution, and again get moving, and we have to shrink the we have to shrink the this CMOS technology. Okay, this is another challenge. Means metal scattering, that is surface scattering, is happening on the copper we use for all the chips. So some chips used by gold also, they are very expensive. Some chips are usually used copper in the network processing units and all. It depends on the technology, and sorry, it depends on the industry line it is. Okay, where it is required like that. So coming to material challenge, there are so many materials are coming up also. The people are finding out, material scientists, graphene and graphene surrounding metals can reduce the skin effect. So this is how the solution is found to reduce the skin effect, because the higher frequency are going gigahertz. So gigahertz will only, when the metal is there, it will not use its core, it will only go on the surface, right? So that skin effect is we have studied in the textbooks. So there are so many challenges are coming up when the technology is getting shrunk. Okay, this is a roadmap of integration in the industry. If you look at from the 2008 to 2020 versus the volume production, we have started. This is given by the ITRIS. ITRIS is the one organization where they make the roadmap of the every electronics that we are going in the industry. So we started using interposers. That is means stacking of the chips one above the other instead of horizontal. Horizontal will make our electronics so big. Otherwise, our laptop wouldn't have been made it without this kind of vertical stacking of the components. So that's called using of the interposers is another one. That is where it will connect the top chip to the bottom chip. This is called interposer. Passive means it will not have any electronics, means transistors inside. Okay, but in active means it can have the logic sitting inside in the interposer itself. What you can see here, between the like this bigger one and smaller one here, these are the interposers. So like this, using these interposers, we can stack them and make the vertical scrapers in the logic ports and the electronic ports, so that more number of chips are put in that in the smaller area. This is called packaging side actually. Even though integration with the FinFETs, everything is happening at the transistor level, this is also happening at the of the packaging side, so that more electrons can be integrated. Okay, coming to the what are the chip digital components. Okay, they will have, I have shown you one of the analog block where analog components are, that is called SerDes IP and GPIO IP, and okay, and the IO pads and memories all will come under, some of the, digital components also, that's called memory SRAMs, sequential cells, combination cells is all as a digital component. Okay, coming to the base layer, FEOL, what we call, it will have CMOS transistors, where CMOS is, it will have NMOS separately and PMOS separately. Together it is complementary metal oxide semiconductor. All the standard cells and IOs will be with this, and resistors will be there, capacitors will be there, made up of the same materials, uh, inductors, and TSV passive and active components. TSVs are passive, and other active components are like switching, whichever switching, that's all are active components. For example, all the flops. Okay. Coming to the metals interconnects, TSVs, and again I have put passive components as well. Metal interconnects will have the components like power mesh separately, clock and signal interconnect separately. Okay, when you say clock and the signal, again the global, intermediate, and local connections are separate. If you do the cross section of a chip here, as shown in this typical on-chip interconnect system, um, the lower layer is a base layer, that is our silicon. In that, transistors are formed here. Okay, after this, metal routing is done. This is what you can see in green color. These are all sitting metal 1, metal 0. I shown in that previous demo, metal 0. And after that, via will come, and after that it will connect to the horizontally, means this vertical horizontal connection, Manhattan routing, and this is only advantages to them because of the manufacturability and other big topic that we can talk, why we have to go for this kind of routings. Okay, so this is how the chips are made with the different metal layers. So locally, very next sitting transistor, if it's talking each other with the help of these metals, that's called local interconnects. And after that, clock will be almost drawn in the intermediate metals. If you see these metals, right, widths are different. When we go towards the top, they are becoming very big in cross-sectional area. That means that the resistance is decreased for them, and local means the resistance is completely increased for them. There are some advantages, disadvantages why we have to do this. Okay, so let's just check means our what are the this chip components and how the chip will be there inside. After that, it will connect to the passivation. After that, these will be connected to the bumps. These are the micro bumps where we'll have the flip chip bumps, and after that it will be packaged and put on the motherboard. Coming to the libraries, okay, we call these all components digital comps as a libraries. That's called standard cells will be there, IOs will be there, outputs, and memories. Okay, in combinational cells of the standard cells, again divided in combinational sequential. So and physical only cells, and there are some special cells also. So combinational will have NAND, NOR, basic AND gates, okay, OR gates, buffers, inverters, clock buffers separately, because this will have equal rise and fall every cell, okay, than the normal buffers here. So both are required. While building the clock, we have to use the clock buffers so that our pulse width can be maintained, and so many reasons. Okay. Delay buffers are there to fix the hold violations. Muxes will be there to channelize the signals, adders, comparators, ECO cells. Sequential cells will be usually only D flip-flops and multiple flip-flops, and D flip-flop with the scans and latches. Latches also will be there as a sequential cell. Special cells like fillers, metal fillers, D cap cells, end caps, well taps. I shown end cap cells. Well taps will be another type, and tie cells and diode cells. These are different cells that we use as a part of our strip cell. Physical only cells or the TCD cells, ESD cells I have shown you. These kind of cells will be there as a phantom cells where they don't have any connectivity. If you click on them, they will just have as their physical presence there, but they are required to get the yield and get connected. ESD cell I didn't show you. It was connected up in the metal 13. Up to metal 13 is completely blocked. It is a self-contained up to metal 13. So that's why that's how ESD can be stopped in even block inside again. And we know there are three types of ESD models: machine model and machine model and and a human body model, and another one is charge device model. Okay, so like this, there are again different voltages for assigned to that. That if the chip is touched by anybody or any machine, so it should not get destroyed. Because of that, we take care of making those chips the ESD protected. Okay, coming to IO pad cell, these are the IPs. IO pad cell are completely self-contained. Here we just make them to just put them in the around the digital block and then get connect the outer world. So these are again IPs, you can see. Memory is also IPs. Register files. The TCAM memories are used usually in the network processors like in Cisco, where these are the ternary. This full form is ternary content addressable memory. So this is used usually for huge memory addressing packets. Okay, and the images. Okay, so these different memories are there. It's a big. We can talk more on these actually. Lecture. Okay, coming to back to 3D view of the single chip. Okay, if you do cross sectional, or if you want to look at the one IC, so it will look like this. It will have, I say, FEOL. FEOL means where the transistors are formed. This front end of line form is. BOL means back end of line, where all the metals will sit like this. See, completely routed here, three-dimensional. You can see 3D view. It will look like this. Okay, so coming to the right side, it can look like this. Okay, the metals. These are the vias, smaller one connection from pillar like. Okay, the same like our civil structure, civil houses are built like one layer after the layer, and these are the kind of pillars. So these pillars are nothing but here conducting metals. Okay, bottom layer, top layer. Okay, like this. Coming to introduction of 3D ICs. Okay, from 2D IC, two-dimensional. When I say 2D, two-dimensional, to the 2.5D we went on, and 3.5D is the next coming up, new technology. But already people are making it, where the HBMs, hybrid memory, HMC, hybrid memory queue, high bandwidth memories. This all comes under 3D ICs now. Realized in the industry, we directly use them as sitting next to each other in the 2.5D. For example, here this is two-dimensional IC. We just know these are the chips, and these chips will have the this round color. This one bumps. This is called the flip chips. Okay, this will just sit on the top of the board. So when we say 2.2D, there are just the wire bonds are used. 100 to 110 to 100 where I was were there per mm square, and power was greater than just 1 to 1.5 picojoules per bit. So when you say 2.5D, we started using micro bumps instead of the flip chips now. C4 bumps. C4 bumps are equal to flip chips. So micro bumps are still smaller than that. So wherein we started integrating more IOs, means more pin density, 1000 to 10,000 IOs per mm square. Power is usually definitely it will go more than 0.5 picojoules per bit, and this higher than this means it may go to where up to means the limit of the power budget. Okay, where we can manufacture. Otherwise, it goes like 400 watts, 500 watts, kind of a huge power consumption. So in 3D, there again micro bumps are used. Die-to-die bonding is used. Wafer-to-wafer bonding can also be done. Where it is now the pin density is too huge, more than 1 million IOs per mm square, from 10,000 to 1 million. Power is still again more than this much only. So when you say 2.5D, the structure is like this. Slice 1 and slice 2 you can see here. So these are completely separate two dies. Okay, one chip is separate, another chip is separate. These two are getting connected here with the help of interposer here. This is called silicon interposer. Okay, these are getting routed here like this. If you zoom in, it will be connecting like this. These two talk like this, one chip to the other chip with the help of TSV. This is the TSV where it will get connected to the package. This is called package substrate. Okay, after this encapsulation will happen, and after that only it is ready for the putting on the board. On the board, the main connection will happen through the BGA solder balls. Okay, ball grid array full form is. So through that, here also some routing will happen. It's called package substrate. After that, another set of this one. These are micro bumps, interposer, and two chips or 3-4 chips can sit on the two planar there, but they're sitting next to each other, where they even talk one hierarchy in the same vertical layer. But when you come to 3D, there are two types again. One is monolithic IC and another is heterogeneous 3D IC. Heterogeneous means we can keep the two chips, like one is processor, another is completely memory, where processor requires a memory to talk and keep the data and come and take it back and process it and send it back to the other rest of the electronics. So like this, it can be completely vertically stacked with that's called heterogeneous. Means we use different RF separate chip, memory separate chip, MEMS separate chip. Okay, this can be done in as a called heterogeneous, because all the different chips can be in the different foundry also. In one foundry we can just assemble. Other one comes in monolithic, where one layer is formed. After that only through the silicon vias are formed. After that next layer is formed. Even though it is processor memory, but in the same foundry we have to make it. We cannot now take another chip by somebody and then put it just like that. We have to grow one after the other. This is called monolithic. This will reduce number of TSVs, interconnects, and technology will be same. Here the technology can be one is 7 nanometer, one is 10 nanometer, one can be 14 nanometer. But here the all will be have to be same, unless we match the power in, very properly supplying to that chip. Okay. Okay, so then question comes, if it is 2D plus 2.5D plus 3D altogether, will it be 7.5D? No, exactly, but it is all called as a 3D IC, because the complexity is only got increased. Coming to the more inside the 3D integration, how exactly this 3D integration is happened when the TSV or TSV is a new terminology and formation of the interconnect instead of the horizontal metal what we used in the routing. Okay, this is called through silicon via. So with the help of this, one die, second die, third are getting connected. These are just interconnects, okay, like pillars, and passing the electrical connectivity or thermal connectivity. When you integrate more number of IOs, that is means pins are integrated more inside the same area, and hence more switching will happen inside the circuits, hence more power is consumed, and thermal is a big issue. So we'll talk about that later. What are the advantages and disadvantages of going for 3D IC or 2.5D IC? Right side is the 2.5D IC, wherein see die 1, die 2, die 3 are horizontally placed. With the help of interposer, it's a more clear picture how TSVs are talking to the SIP substrate and then circuit board. Okay, it's just a difference more the cross-sectional area. This doesn't have interposer here in left side, which is true 3D IC form, even though we use exact TSV. Even though right side we use TSV, but it's not true 3D IC. It is having interposer here, where the interposer can be a bigger structure here. It will not have any circuit sitting inside. Okay, this is again more about how the connectivity is done. For example, in the 3D IC, if you take zoom in, so it will be connected like this. One die 2 is here, and die 1 is at the bottom, and this is one TSV. This is the micro bump. Through this, it will be get soldered, and next layer another TSV will be there already sitting in the BOA layer. This is face to back connectivity. Okay, face to face means this BOA layer come here, and again this will be get connected, and that way, accordingly, the TSVs are formed. It is shown only for one example. So these are the transistors. This is PNP or NPN transistor, where it is having 3 nodes here, and that connect to the TSV. Okay, like this here, right side. So this how this is now TSVs and 3D integration and all those terminology will come into picture. Okay, what are the implications and challenges of 3D IC? When you say challenges, nothing but our disadvantages. For example, when we make the 3D IC, the thermal issue will come, because I said just now, because of the high intensity, high power consumption. So that is disadvantage of it. But if we solve this, this is our challenge. Okay, to solve address the issues of 3D IC itself is our new challenge and make this happen. So yield challenge is there. For example, yield means here all the chips inside one 3D package should all be working, right? If one is working, though, we have to throw away the remaining two still working. We have to throw complete chip, right? That's a yield challenge is there. And yield means here one after the other the connection is done. They have to check it and then only take to the next integration level, second, third chip integration, so that first two are working. Now third can be introduced and then that one taken as a one component. Like that, one complete product they will make. So yield challenge a big one, and reliable challenges, because reliability is nothing but it should work for at least for if you bought it today, the TV, the next day it shouldn't, it's not working means it's not reliable. So it should work for at least how many numbers of years we designed it, at least for 5 years, 10 years, so it should work. So reliability is a big issue again here in the 3D because of the power challenge. There may appear some cracks and all those things that will make it unreliable, means it will not work. If the thermal management is failed by unfortunately, then the 3D will have such kind of issues. Okay, testing and fault tolerance of the 3D is another one, where because DFT testing is a big ocean, where they have to make sure that every part is working, then only it can do the magic. So everywhere it should be testable, and should have some fault tolerances also, so that can have spare TSVs or spare memory, so it will start working. So such arrangements also should be there. So these are all the disadvantages actually. So but these becomes a challenges to solve for the further growing inside as a 3D integration. So coming to the advantages, if you make this very working properly, so we have high value production means low cost will be there, and very good uh, this is very good that we have solved it in the way that we require. Hello. Okay. Coming to the massive I/O interfaces, this will improve the bandwidth, because in the local small area we have introduced a massive input outputs. And other things is heterogeneous integration is possible, and reduced real estate area, because we are growing it in vertically, and improved performances and high performances that we can see with the help of 3D ICs. Okay, coming to the evolution of transistor in the industry. So what is happening? We have seen two planar FinFETs in our college days that we studied. So that means it was a buried transistor. Buried means where the source and drain were inside the same substrate. Gate was also inside it. So gate was completely buried inside the transistor. That's called MOSFET, right? So now FinFETs are coming. This is called FinFETs are nothing but the 3D. I mean, now gate is come out of this buried dome and sitting here like this. Okay, source drain will be still buried here. So this is one evolution that we started with, because why it has come out, why we have to make this way structure, because now gate is the only controlling the channel when the depletion region is formed, right? So we have now only one uh, area only we supposed to, we were controlling it. Now we have three areas, left, right, and top. So if you metalize this complete three, so this whole gate can be completely very well. Means switching fast and switching off fast, switching off and switching on can be controlled very fast. So that's how improvement happened. So after that, what happened now? Source and drain also come out of the buried silicon. So now this become a ribbon FETs. Okay, so ribbon FET technology leaded into the third portion here, as you can see. This becomes source, drain, and gate. This whole set of three transistors are formed here. 1, 2, 3. Source, drain, gate. Source, drain, gate. But with a multi-bit, controlling can also be done with a multi-bit, flip-flops or that we make in the transistors, right? That's how the evolution of in the industry. This is called 3D transistors. In the transistor level also, this has started growing up. So the right side is planar versus FinFET differences. They just talked about this was buried, and now this started growing outside. And now no more substrate is remaining only for just supporting the gate. Okay, this is called gate all around. Means here gate is now controllable all the four here, right? Four sides. 1, 2, 3, bottom also and top also. So like this, quick performance of the transistor can happen. Instead of slow switching, slow switching activity, on and off will be faster, so faster when we take to this kind of structures. So this is called FinFETs or ribbon FETs. Okay, and gate all around FinFETs. From the gate, only three sides of the FinFETs. So like this evolution is happening. So when we come to the IP or standard cell design, this is getting like this in the FinFETs. So previously in 15, the two planar buried transistors were looking like this, before 2015, and after that we started with this FinFETs were taller, and now the size of size of the row is now came down. So in one row it can be still but still taller, but it is again FinFET. Okay, one after the other. This integration of this is a color what you say schematic that shown on the VLSI design of the standard cell, because the one poly and left side, when the poly is drawn, the source and drain will be formed like this. Right. So like this, when it comes to the gate all around, it is still shrunk in terms of the height as well as the width. The width is completely came down because now one transistor is sitting beneath it, right? So all the CMOS at the top, sorry, PMOS, so now will be all sitting beneath it. So we cannot show it in the two planar anymore here. Just understand this. So in 2028 it will be still lesser because of this ribbon FinFETs will still go in the different formats, and the evolution is happening. Okay, so like this in transistor level, these are all in the standard cell wise, these sizes will also come down. Okay, coming to the physical design activity of the chip, how the chips are made, RTL to GDS. We saw design entry with the help of Verilog coding. Those designers will write the Verilog coding as per the specification given, as per the applications that the chip is going to be made. So after that, we synthesize it in the DC. After that, we take to the place and route tool, that's Innovus or ICC2. After that, we do physical verification, metal fill, that is nothing but our DRC, everything is clean, that is manufacturability, DFM, DFY, design for yield, those checks it will cover under this. After that, we do extraction. Extraction is our real real RLC is calculated. After that, timing, whether setup hold, our transition issues, pulse width modulation, pulse width issues, and all those if they are met, then this is ready for our tape out. But before that, we do so many iterations because we just fix one, and after that again we check for timing. At that time timing, if setup is met, hold is not meeting, we again take back to the place and route. We change this in the layout here, what we see in the right side, and take through all this, and that's how one final day this will be completely free from all the violations, and then it will be for the tape out. This is how we just saw the layout will be the chips and memories and bumps also I have shown. So this is complete top layer. So IOs are placed here like this. Here you can see top and bottom, and this is the corner IO chip here, the square shape, all four sides square. So this is the flip chips. So these bumps, these are the this is called RDL, redistribution layer routing, where this chip, these bumps will be internally connected to the IOs like this. This IOs will be internally, and the beneath this, all the standard cells in core area, different blocks will be, they will be talking. So like this whole chip is made. Coming to this, why we call it as a placement and routing. In between that, block tree is also there. When the Verilog or HDL is entered, so the netlist is formed like this in the textual format I have shown. If you draw it, it will be like this, looking like this as a circuit. And after that, this system partition is done. And after that, chip is, this system partition means in our chip, we just make some portion, some memories to sit here, and as per that logic will sit there, related talking logic, and next module will sit if the module as per the data diagram, data has to go from one module to another module. As per that, we have to make this floor plan. It's called a floor plan step. After that, we do a complete placement and routing, and after that we do complete chip finish. So they just block level and logic cells they have shown by taking one by one. Here the logic to the one chip portion to the rows here, and inside the rows one standard cell they have shown. Okay, coming to the floor plan. In the floor plan, what we do, we make the tracks first, we make the rows, and we create the grids for that, rows, cells, and instances. Okay, these are the terminology that we need to know in the time of floor plan. Macros means our memories. Attributes of the cell, polygons means our metals, uh, devices, and texts. Okay, these are the things that we should know at the time of floor plan. And after that, boundary box definitions, pin and port placements we need to do here. As per that, again the related logic will set to talk to that IO port. Okay, so regions, fences, and groups are again different things that we need to make the partition inside the chip. That's called the complete floor plan. So PG grid will be drawn. After that, metal stitching it is completely from top to till the lower layer of the metal where the standard cell will be formed. That with the help of in the baking source drain gate inside the base layer. Coming to the placement, there are placement standard cells SVT, LVT, ULVT. Nowadays in 5 nanometer, extreme LVT, ELVT, EULVT will come. So that means these are different variation of the cell where it will have same footprint, but uh, the delays will be different. SVT will be more delayed, but it will have consumed the less leakage power. Leakage power will be less. When we go to the lower technology, leakage is the big issue because of the sub-threshold voltage, and HCI, that hot carrier injection, is another big ocean. Cat in the IEEE papers, and NBTI and PBTI is another big ocean, which are causing the more leakage towards the lower technology nodes. So because of that, the delays will they will use more power, but they will unnecessarily produce huge leakage power, and because of that, so many disadvantages will happen, and performance will be reduced. More power is consumed, even though we start to make it more integrated, but that's why these types of different cells are used. We will swap the ULVT with the SVT where the leakage can be stopped with the same set of AND gate. For example, the AND gate in ULVT version, we can swap to SVT version as per the timing meeting setup time. We need to swap with SVT with ULVT because we have to make the data or clock to be fast. So like that, okay, for the skewing or something. So there are so many logics in that to doing that. That's why these types of cells are there with the same set of AND gate or NOR gate, whichever inverter or something. So ideal clock, timing optimization and legalization of the cells, and optimization iterations like timing DRV, designed for verification. That is nothing but our transition violations and the congestion of the metals. All needs to be taken care at the time of placement. So timing power, scan reordering also happens at this time because of the DFT has to be stitched to test all the all the components of this logic. So before the chip is used, so those all will be taken care at the time of placement. The place design will look like this with the help of macros here, power structure here. Okay, coming to the routing. So routing happens like this. This is one cell. I have taken snapshot from there. This will be connecting the Manhattan routing. So one vertical, and after that is a horizontal routing, and get connected to this pin. From B pin of this cell connected here, A pin of this, another U17 as a cell name. Like this. So track assignment, global routing, and detailed routing are the steps soon after the tool starts working on it, because track assignments, what it will do is, till first it knows where the logical connectivity is there between this to this in the netlist. So it has to connect now with the help of metal. So first it will take vertical one big router here, routing polygon. After that, it go on refining it. That's called first it's called track assignment. After that, global routing, means it starts taking one portion of it and starts a little bit working on it. And detailed routing, it exactly connects like this. Okay, it will not completely connected at the time of global routing or track assignment. It will just make the assumptions of this. And there's an algorithm that one can develop how the tool has to work to get it routed. Yeah, there are so many things in the routing. So search and repair will clean up the extra metal here created by the tool or DRC antenna violation cleaning. Such thing will happen in time routing and routing optimization. After routing is done, the extraction of the metals has to be calculated and cell delay has to be calculated exactly. So it will happen just by not placing them and routing them. But another tool comes into picture that's called star RC XTR Quantus from the Cadence star RC from the Synopsys. These will calculate exact in the spec format. So this all the PVT corners, process voltage and temperature corners of AVCV and all those will be applied. And then in prime time DMSA is the one distributed prime time. So the STA timing will be calculated exactly noise violations, X-talk violations, crosstalk violations, DRV. All those will be fixed by doing the iterations after the iteration to make the database ready. Okay, if you look at this structure, I think I just shown in the already. This is one memory. Is a single port memory because only pins are one side here. Single port. Dual port means here also pins will appear in the right side also. So this is talking to. I just highlighted one path. One register is to mem violation is shown. So it is talking like this because why it is the snake-like path is the actual routing happened like this in the metals. Okay, if you look at the 3D view, I didn't show you 3D because it takes huge time to load it. We don't work on this just for the visualization, but we only work on this where it is very faster to understand and from the top level view and then to close the timings. Okay, demo is already shown. So in the demo we have seen physical design block level reviews, on-chip components also one by one, and viewing of the directories in different stages of the RTL2 GDS2, and we also checked some of the basic Unix and Linux commands. Okay, summary and conclusion: knowing the electronic industry and present technology advancements, it is done, and technology challenges. What are they available now? So one can take and work on. And stages of the physical design of a chip, we have just seen it. And physical designing of a chip in an industry with a Unix environment, we also seen it. Yeah, I think that's all I have from my agenda today. I think I have finished 2 hours 12 minutes now. So we'll take any QA if you have that I can try to answer. Sir, madam, please can you bring up some questions that I can try to answer?
Hello, sir.
Yes, sir.
Hello.
Tell me, sir. Yes.
Sir, in some papers they are giving 7 nanometer node and 7 nanometer channel length.
Okay.
In my trial paper, I observed 7 nanometer node, but channel length they are taking 13.5.
Okay.
Sir, which one is correct, sir? Channel length is correct word or channel node is correct word?
See, when they say technology node is 7, maximum it can go up to 8. Okay. 7 means 8 to 11 also we have seen in the TSMC libraries. Okay. When they say TSMC 7 nanometer, we have libraries of 8 nanometer, okay, and 11 nanometer also. But it shouldn't go up to 13. Actually, it could be a wrong. So channel node is correct actually. So approximation they do. Okay. In the 5 nanometer, I am working on it presently, sir. I tell you, we are seeing channel length as 6 nanometer only. It never be 5.
Not audible.
So,
Hello.
yeah, hello. Can you hear me? Hello.
Sir, yes, sir.
Sir, audio cutting, sir. Please repeat. No?
Yes, sir. See,
5 nanometer channel length you are telling.
Yes, in the 3 nanometer, in the 5 nanometer, I'm telling actually in the 5 nanometer I'm working on. So I am seeing all the standard cells having the channel length as 6 nanometer only, and but they TSMC named it as 5. So approximate near about things actually in the real industry. So 5 nanometer means 6 nanometer exactly that the channel length is exactly 6. But in the 7 nanometer, what happened? We have combination of 6 plus 11 also. Hello.
Okay.
Hello. Sorry, in the 7 nanometer, we exactly had the combination of 8 plus 11. Okay, some standard cells were having 8, some standards were having 11. So our job even used to calculate how many channel length of 8 have been used, how many channel length of 11 also has been used. We try to minimize the 11, but we try to use the more of 8. If we use more of the 8 channel length, we have more leakage powers. So 11 nanometer, we are doing better in the so we use such combination of standard cells also, but it is still 7 nanometer. Hello.
Okay, sir. Sir, depends upon standard cell. You can say that which node it is.
Yes, we can say. But just by reading the name of it also, we can say which nanometer it is.
Okay. Still, on the paper title, they are telling 7 nanometer. No. But inside the paper, they are wearing like what you told, 8 nanometer, 11 nanometer, like that.
Yes, sir. That will happen. Yeah. But 13 is too much. They shouldn't use 13. Maybe up to 11 they can go for, because I have seen in the industry TSMC we taped out to that technology, and it's all in mass production also, where Google and Facebook are our customers for using that. Yeah.
Okay. Sir, another question.
Yes,
If there are any other questions, you can ask.
Hello.
Okay. Like you can find the feedback link for afternoon session in the chat box. You can please fill it. On behalf of Department of Electronics and Communication, BIT, I extend my most sincere thanks to our eminent speaker, Mr. Chandrasekhar Patil, who has shared his profound knowledge and given a demo on Linux commands and 3D IC components. Thank you very much, sir.
Yeah, thank you very much. Yeah, it's my pleasure.
Okay, we can wind up for the day. Thank you all. Good evening.
Thanks to all.
Thank you, madam.
If you have any questions,